Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the silent vigil that humanity maintains against the ancient wanderers of space. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the high desert of Arizona, where the Sonoran landscape stretches toward distant mountains and the air grows thin with altitude, a telescope moves with mechanical patience through the darkness. The Catalina Sky Survey's cameras sweep across predetermined coordinates, their electronic eyes opening and closing in measured intervals. 4 images of each patch of sky, spaced precisely 15 minutes apart, accumulate in digital memory like astronomical time-lapse photography. Stars remain fixed in their positions, their ancient light steady and unchanging across the brief span of an hour's observation. But sometimes, between the first frame and the fourth, a single point of light shifts its position by mere pixels. This movement, barely perceptible even to sophisticated pattern recognition software, marks the presence of something that has wandered into Earth's gravitational neighborhood, an asteroid, perhaps no larger than a few city blocks arranged end to end, drifting through the vacuum on a trajectory that will bring it within 30 million miles of our planet. The discovery happens without fanfare or celebration, simply the automated registration of coordinates, the assignment of a preliminary alphanumeric designation, and the quiet addition of another entry to humanity's growing census of near-Earth objects. Within hours, the detection appears on astronomical bulletin boards and notification systems, where it joins thousands of similar discoveries made each year. The asteroid itself remains entirely unaware of its newfound significance to human civilization. For 4.5 billion years, it has followed its elliptical path around the Sun, a fragment of the early solar system's construction debris left over from the epoch when planets were still assembling from the primordial disk of dust and rock. Its surface bears the accumulated scars of countless micrometeorite impacts, each collision adding another microscopic layer to its complex geological history. Cosmic rays have altered its surface chemistry over geological time, darkening its exterior until it reflects only a small fraction of the sunlight that strikes it. Solar heating causes thermal stress fractures to propagate slowly through its interior, creating a rubble pile held together by its own weak gravitational attraction. Only now, as it approaches the inner solar system once again on its predictable orbital cycle, does this ancient wanderer encounter the patient, systematic gaze of human instruments. The discovery represents a moment of intersection between two vastly different timescales, the billion-year story of an asteroid's existence and the few decades span of humanity's technological ability to detect and track such objects. In astronomical terms, this intersection occurs in an instant so brief as to be essentially instantaneous. Scientists estimate that fewer than half of the near-Earth asteroids larger than 140 meters across have been discovered and catalogued. The remainder continue their ancient orbits in complete obscurity, their existence known only to the gravitational forces that guide their motion through space. Some will remain hidden for decades or centuries more before crossing the narrow field of view of Earth's expanding network of automated survey telescopes. Others may have already passed their closest approaches to our planet during previous orbital cycles, retreating into the outer reaches of the solar system without ever registering on human sensors or appearing in any database. The mathematics governing these celestial mechanics operates with impassive, clockwork precision. Newton's laws of motion and universal gravitation describe asteroid trajectories using the same fundamental equations that predict the orbital paths of planets, moons, and comets throughout the solar system. Given sufficient computational power and accurate initial measurements, an asteroid's future position can be calculated years or even decades in advance with remarkable accuracy. Yet, within this apparent mathematical certainty lies an element of chaos theory that introduces subtle but persistent uncertainty into long-term predictions. Tiny perturbations in an asteroid's orbit, caused by the gravitational influence of planets during close encounters or the gentle but relentless pressure of sunlight on its surface, accumulate over time into significant changes in trajectory. The Yarkovsky effect, named after a 19th century Russian engineer, describes how absorbed sunlight re-radiated as heat from an asteroid's surface creates a small but persistent thrust that gradually alters its orbit. An asteroid's future position, predicted with high confidence for the next few decades, becomes increasingly uncertain when projected centuries or millennia ahead. This mathematical limitation means that asteroid impact predictions become essentially meaningless beyond a few hundred years. The catalogue of known near-Earth asteroids grows steadily each night as automated systems process the previous evening's observations. Each new discovery begins as nothing more than a series of coordinate measurements, right ascension, declination, and apparent magnitude recorded at specific times. From these basic data points, orbital mechanics specialists derive the object's three-dimensional trajectory through space, calculating its semi-major axis, eccentricity, inclination, and other orbital elements. The asteroid receives a permanent numerical designation only after its orbit has been determined with sufficient precision, a process that may require months or years of additional observations. Most newly discovered near-Earth asteroids pose no conceivable threat to Earth. Their orbits carry them past our planet at distances measured in millions of miles, close only by astronomical standards. The vast majority earn a classification of 0 on the Torino Impact Hazard Scale, indicating no cause for concern. They join the growing population of catalogued objects that serve primarily as subjects for scientific study rather than objects of planetary defense concern. Only a small fraction, perhaps 1 in 1,000 discoveries, merits closer examination and more frequent observation to refine trajectory calculations. The patient work of asteroid detection continues each clear night, weather permitting, across multiple observatory sites chosen for their dark skies and stable atmospheric conditions. Telescopes in Arizona, Hawaii, New Mexico, and other locations contribute to a coordinated global effort that never truly sleeps. When clouds obscure the view from one facility, others continue the systematic survey of celestial coordinates. The search pattern gradually covers the entire accessible sky over periods of weeks or months, then begins again, watching for objects that may have shifted into Earth's vicinity since the previous survey cycle. Each detection represents a small victory in humanity's effort to achieve what astronomers call situational awareness, a comprehensive understanding of the near-Earth environment and the population of objects that share our orbital neighborhood around the Sun. This knowledge serves multiple purposes beyond planetary defense, providing insights into the formation and evolution of the solar system while offering potential targets for future robotic or crewed missions. Some near-Earth asteroids contain valuable minerals and rare elements that may someday justify the expense and complexity of asteroid mining operations. The gentle irony of asteroid hunting lies in its fundamental dependence on the objects remaining predictably visible against the background stars, following the same Newtonian mechanics that govern all celestial motion. The very laws that allow astronomers to calculate precise future positions for these wandering rocks also ensure that most will continue wandering harmlessly through space, their orbits carrying them past Earth at safe distances for millions of years to come. Only a tiny fraction will ever approach close enough to warrant serious concern, and fewer still will actually intersect our planet's orbital path. In the quiet hours before dawn, when the last observations of the night are complete and the telescopes prepare to close their protective covers against the approaching daylight, the accumulated data begins its journey through automated processing systems. Software algorithms examine each image, comparing it against star catalogs and searching for the telltale motion that betrays the presence of a previously unknown asteroid. Most nights yield nothing more than confirmatory observations of already known objects, their predicted positions matching the calculated values within narrow margins of error. But occasionally, the patient search discovers something new, something that has been wandering undetected through the cosmic darkness for billions of years until this moment of technological intersection. The mathematics of celestial motion unfolds across computer screens in NASA's Jet Propulsion Laboratory, where orbital analysts transform raw telescope observations into precise trajectories that stretch across decades of future time. Each newly discovered asteroid begins as a scattered collection of position measurements, coordinates captured on different nights, separated by days or weeks of observation. These data points, when fed into sophisticated orbital determination software, reveal the invisible elliptical path that carries each object around the Sun with clockwork regularity. The computational process resembles archaeological reconstruction, piecing together a complete three-dimensional orbit from fragmentary evidence. Initial observations may span only a small arc of an asteroid's orbital path, perhaps representing just a few % of its complete journey around the Sun. Yet, from this limited sample, mathematical algorithms extrapolate the object's full trajectory, calculating where it has been throughout the solar system's history and predicting where it will travel in centuries to come. The calculations assume that gravitational forces alone govern the asteroid's motion, treating it as a point mass subject only to Newton's universal law of gravitation. In reality, the gravitational environment of the inner solar system proves far more complex than simple two-body mechanics would suggest. Each asteroid moves simultaneously under the gravitational influence of the Sun, Earth, Moon, Venus, Mars, and Jupiter, with smaller perturbations contributed by every other planetary body. The combined effect creates what mathematicians call the n-body problem, a system of differential equations so complex that no general analytical solution exists. Only numerical integration, performed by powerful computers running for hours or days, can trace an asteroid's path through this gravitational maze with adequate precision. The orbital elements that emerge from these calculations tell the complete story of an asteroid's relationship with the solar system. Semi-major axis describes the size of its elliptical orbit, while eccentricity measures how elongated or circular that ellipse appears. Inclination reveals the tilt of the orbital plane relative to Earth's path around the Sun, and the argument of perihelion indicates where in its orbit the asteroid approaches closest to our parent star. These 6 numbers, determined to many decimal places, contain enough information to predict the asteroid's position at any moment throughout its orbital period. Most near-Earth asteroids follow orbital periods measured in months or years, completing their circuits around the Sun in time frames comprehensible to human experience. Apollo-type asteroids typically require between 1 and 4 years to complete a full orbit, while Aten-type objects circle the Sun in periods shorter than Earth's own year, The mathematical precision of these calculations often exceeds the accuracy of the original observations by orders of magnitude, transforming rough position estimates into trajectory predictions accurate to within a few kilometers across spans of decades. Yet this mathematical certainty contains subtle limitations that become apparent only when projections extend far into the future. Small uncertainties in the initial orbital determination, perhaps introduced by atmospheric turbulence affecting telescope observations or systematic errors in measurement systems, propagate forward in time according to the principles of chaos theory. An asteroid's predicted position, known to within a few hundred meters for next year's close approach, may be uncertain by thousands of kilometers when calculated for encounters a century hence. The Yarkovsky effect introduces additional complications that challenge the purely gravitational models used in orbital calculations. This phenomenon, named after Ivan Yarkovsky, a 19th century Russian civil engineer who first described it theoretically, arises from the thermal properties of asteroid surfaces. As an asteroid rotates, its sun-facing hemisphere absorbs solar radiation and heats up during the local afternoon. Hours later, after the asteroid's rotation has carried this heated region into darkness, the accumulated thermal energy radiates back into space as infrared light. This re-emission of energy creates a small but persistent rocket-like thrust that gradually changes the asteroid's orbital velocity. The magnitude of the Yarkovsky effect depends on factors that remain difficult to measure from Earth-based observations: an asteroid's rotation rate, surface composition, thermal conductivity, and bulk density all influence how efficiently it absorbs and re-radiates solar energy. Dark, carbon-rich asteroids behave differently from bright, rocky ones under the same solar illumination. Rapidly spinning objects distribute heat more evenly across their surfaces, reducing the thermal thrust, while slowly rotating asteroids develop larger temperature gradients that enhance the effect. Over millions of years, Yarkovsky thermal forces can produce substantial changes in asteroid orbits, sometimes nudging objects from the main asteroid belt into Earth-crossing trajectories. This process operates on timescales far longer than human civilization, yet its effects must be considered when making long-term impact assessments. An asteroid that poses no threat for the next several centuries might gradually spiral inward or outward under thermal forces, eventually developing a dangerous orbit thousands of years from now. Binary and multiple asteroid systems add another layer of complexity to orbital mechanics calculations. Approximately 15% of near-Earth asteroids exist as gravitationally bound pairs, with smaller companion objects orbiting around larger primary bodies. These systems challenge traditional orbital determination methods, which assume each asteroid behaves as a single-point mass. Binary asteroids exhibit subtle variations in brightness as their components eclipse or occult each other during orbital motion, providing clues to their binary nature but complicating the mathematical models needed to predict their trajectories accurately. Radar observations from facilities like the Arecibo Observatory and Goldstone Deep Space Communications Complex have revealed that many asteroids previously thought to be solid. Monolithic objects actually consist of loose aggregations of smaller fragments held together by weak gravitational attraction. These rubble pile asteroids respond differently to gravitational and thermal forces than solid rocky bodies, potentially exhibiting more complex rotational behavior or structural changes over time. The internal structure of an asteroid influences how it transfers heat from sun-facing to shadowed regions, affecting the magnitude and direction of Yarkovsky thermal forces. Close encounters with planets introduce dramatic but predictable changes to asteroid orbits through gravitational scattering events. When an asteroid passes within a few million kilometers of Earth or Venus, the planet's gravitational field deflects the object onto a new trajectory, sometimes dramatically altering its future orbital evolution. These encounters, known as gravitational slingshot events, can either accelerate an asteroid to higher solar orbits or slow it down, causing it to spiral closer to the Sun. The same gravitational mechanics that spacecraft mission planners use to explore the outer solar system also governs the long-term evolution of asteroid populations. Jupiter, with its massive gravitational influence, acts as the solar system's primary architect of asteroid orbits. Many near-Earth asteroids trace their origins to the main asteroid belt, where Jupiter's gravity creates zones of orbital instability called resonances. Objects trapped in these resonant regions experience periodic gravitational kicks that gradually increase their orbital eccentricity until they develop Earth-crossing trajectories. The process operates over millions of years, steadily supplying new members to the near-Earth asteroid population while simultaneously ejecting others from the inner solar system entirely. The mathematical models used to calculate asteroid trajectories continue to improve as computers become more powerful and observations become more precise. Modern orbital integration codes can account for relativistic effects, solar radiation pressure, and the gravitational influence of individual asteroids on each other. These refinements push the practical limit for accurate trajectory prediction further into the future, extending the time frame over which impact assessments remain meaningful. Yet, fundamental limitations imposed by chaos theory ensure that perfect long-term prediction will always remain beyond reach, no matter how sophisticated the mathematical models become. Each newly calculated orbit joins a database containing hundreds of thousands of asteroid trajectories, all derived from the same fundamental principles of celestial mechanics that Johannes Kepler first described 4 centuries ago. The accumulated knowledge represents humanity's most complete census of the small bodies sharing our cosmic neighborhood, a mathematical catalog of wandering worlds that have been circling the Sun since the solar system's formation. These calculations form the foundation for all planetary defense planning, providing the essential first step in determining which asteroids deserve closest scrutiny and which can safely be ignored for the foreseeable future. Beneath the star-scattered dome of Arizona's desert sky, the Catalina Sky Survey's robotic cameras maintain their methodical vigil with the patience of machines designed for repetitive precision. 4 times each night, these electronic eyes capture the same celestial coordinates, their shutters opening and closing in intervals measured to the second. Between each exposure, the telescope mount adjusts its position with mechanical accuracy, compensating for Earth's rotation to keep distant stars precisely centered in the camera's field of view. The process unfolds without human intervention, guided by software that has performed these same motions thousands of times across countless clear nights. The desert location offers advantages that extend far beyond its famously clear skies and minimal light pollution. At an elevation of nearly 8,000 feet above sea level, the Catalina Mountains provide atmospheric conditions that minimize the turbulence and moisture that can blur astronomical observations. Winter nights bring temperatures that drop well below freezing, reducing the thermal noise in sensitive CCD cameras and allowing longer exposures without degrading image quality. The high desert's extreme aridity means that water vapor, which absorbs certain wavelengths of light and creates atmospheric distortion, remains at minimal levels throughout most of the year. Each 4-image sequence follows a pattern optimized through decades of asteroid hunting experience. The first exposure captures a baseline image of the target sky region, recording the positions and brightnesses of thousands of background stars. 15 minutes later, the second exposure reveals any objects that have moved against this stellar backdrop, their apparent motion caused by their proximity to Earth compared to the vast distances of background stars. The third and fourth exposures, spaced at identical intervals, confirm the reality of any detected motion while establishing the direction and rate of apparent movement across the sky. The time intervals between exposures represent a careful balance between competing observational requirements. Shorter intervals might miss slow-moving asteroids whose motion becomes apparent only over longer time periods, while longer intervals could allow fast-moving objects to travel outside the camera's field of view between exposures. 15-minute spacing has proven optimal for detecting the majority of near-Earth asteroids, which typically exhibit apparent motions of several arc-minutes per hour as seen from Earth-based telescopes. Sophisticated software algorithms examine each night's accumulated images, searching for the telltale signatures that distinguish moving asteroids from the static star field. The computer programs must differentiate between genuine asteroid detections and various forms of false positives, cosmic rays striking the camera detector, aircraft or satellites crossing the field of view, and electronic noise or defects in the imaging system. Machine learning techniques, trained on millions of previous observations, have become increasingly sophisticated at making these distinctions automatically, flagging only the most promising candidates for human review. The sheer volume of data generated by modern asteroid surveys challenges even advanced computational systems. A single night's observations from the Catalina sky survey might produce several terabytes of digital imagery, each image containing millions of individual pixels that must be analyzed for signs of moving objects. Automated processing systems work through these datasets during daylight hours, when the telescopes remain closed and protected from the harsh desert sun. By the following evening, the previous night's discoveries have been incorporated into the global database of known asteroids, their preliminary orbits calculated, and their potential threat levels assessed. Weather patterns in the Sonoran Desert follow seasonal cycles that astronomers have learned to anticipate and work around. Summer months bring monsoon conditions with afternoon thunderstorms and increased humidity that can render observations impossible for days at a time. Winter brings the clearest, most stable atmospheric conditions, but also shorter nights that limit the total observing time available for asteroid surveys. Spring and autumn offer intermediate conditions that often provide the most productive observing seasons for systematic sky surveys. The remote location of most asteroid survey facilities necessitates careful planning for equipment maintenance and repair. Spare parts, backup systems, and technical support must be readily available to minimize downtime when critical components fail. Desert environments prove particularly challenging for sensitive electronic equipment, with extreme temperature variations, dust infiltration, and occasional sandstorms that can damage exposed optical surfaces. Preventive maintenance schedules account for these environmental factors, with regular cleaning, calibration, and component replacement performed during planned maintenance windows. Light pollution from distant cities creates subtle but measurable effects on the sensitivity of asteroid detection systems. Even the relatively isolated Catalina Observatory experiences some degree of sky glow from Tucson's metropolitan area, located roughly 50 miles to the south. This artificial illumination raises the background light level across the entire sky, reducing the contrast between faint asteroids and the night sky background. Survey teams must constantly balance the trade-off between proximity to urban centers with their technical support infrastructure and the pristine dark skies needed for optimal asteroid detection. The asteroid discovery process transforms raw astronomical observations into carefully validated scientific data through multiple stages of verification and refinement. Initial detections by automated software represent only the beginning of a process that may require weeks or months to complete. Follow-up observations from multiple facilities confirm the reality of each new object, while orbital calculations determine whether it belongs to one of the categories of potentially hazardous asteroids that warrant continued monitoring. International cooperation plays an essential role in modern asteroid survey operations, with observatories around the globe sharing data and coordinating observations to maximize sky coverage and minimize duplication of effort. The Minor Planet Center, operated by the International Astronomical Union, serves as the central clearinghouse for all asteroid and comet observations worldwide. This organization maintains the authoritative database of orbital elements for all known small solar system bodies, assigning permanent numerical designations to objects whose orbits have been determined with sufficient precision. Professional astronomers estimate that current survey programs detect approximately 3,000 new near-Earth asteroids each year, adding to a catalog that now contains more than 30,000 confirmed objects. This discovery rate continues to accelerate as new survey telescopes come online and existing facilities upgrade their cameras and detection systems. Yet, the task of achieving comprehensive situational awareness of the near-Earth environment remains far from complete, with perhaps an equal number of undiscovered asteroids awaiting detection by future surveys. The Catalina Sky Survey represents just one component of a distributed global network of asteroid hunting facilities that includes Linear in New Mexico, NEOS in Earth orbit, and numerous smaller programs operated by professional and amateur astronomers. Each contributes unique capabilities and sky coverage to the overall effort, creating a comprehensive monitoring system that operates continuously as Earth's rotation brings different regions of the sky into view from various observatory sites. The gentle irony of modern asteroid hunting lies in its complete dependence on technologies that would have seemed impossibly sophisticated to astronomers just a few decades ago. Digital cameras sensitive enough to detect asteroids millions of miles away, computer networks capable of processing terabytes of data nightly, and orbital calculation software that can predict trajectories decades into the future. Yet the fundamental challenge remains exactly the same as it was for the first asteroid hunters 2 centuries ago, distinguishing the subtle motion of nearby objects against the apparently fixed background of distant stars. One careful observation at a time. As each night's survey work concludes and the telescope enclosures close against the approaching dawn, the accumulated observations join an ever-growing archive of human knowledge about our cosmic neighborhood. The patient, systematic scanning of the night sky continues year after year, expanding the catalog of known objects and gradually approaching the goal of comprehensive awareness of everything larger than a house that shares Earth's orbital vicinity around the Sun. The asteroid drifts through the vacuum of interplanetary space, following an elliptical trajectory that has carried it around the Sun more than 1 million times since its formation 4.5 billion years ago. Its journey began in the primordial disk of dust and rock that surrounded the young Sun, where countless collisions and gravitational interactions gradually assembled the planets and left behind a population of smaller debris. This particular fragment, roughly 300 meters across and shaped like an irregular potato, survived the violent early epochs of solar system evolution through nothing more than statistical fortune and the vast emptiness of space. For eons beyond human comprehension, it has maintained its solitary orbit, neither approaching close enough to any planet to be captured or ejected, nor colliding with other objects despite sharing the inner solar system with thousands of similar wanderers. Its surface bears the accumulated record of this journey: impact craters from micrometeorite bombardment, fracture patterns created by thermal stress cycles, and chemical alterations produced by billions of years of exposure to cosmic radiation and solar wind particles. The asteroid's irregular shape results from its violent birth during the catastrophic disruption of a much larger parent body sometime in the distant past. When gravitational perturbations or a major collision shattered the original object, this fragment inherited a complex rotation that causes it to tumble end over end as it travels through space. The rotation period, approximately 6 hours and 27 minutes, ensures that all portions of its surface, experience cycles of solar heating and radiative cooling as it spins through the harsh temperature extremes of the space environment. Its composition reflects the cosmic chemistry of the early solar system, with silicon and oxygen forming the dominant minerals in its rocky matrix, while traces of metallic iron and nickel create small inclusions scattered throughout its interior. Spectroscopic analysis from Earth-based telescopes suggests it belongs to the S-type asteroid class, indicating a composition similar to ordinary chondrite meteorites that occasionally survive atmospheric entry to reach Earth's surface. This classification places it among the most common type of near-Earth asteroids, objects that formed in the inner regions of the asteroid belt, where temperatures were high enough to prevent the condensation of water ice and other volatile compounds. The asteroid's orbit carries it on a path that intersects Earth's trajectory around the Sun, earning it the designation of a potentially hazardous asteroid despite the low probability of an actual collision. Orbital mechanics calculations reveal that its elliptical path brings it within approximately 2 million miles of Earth's orbit at regular intervals, close enough to warrant periodic observation and trajectory refinement by asteroid tracking programs. Yet, the three-dimensional geometry of orbital motion means that Earth and the asteroid rarely occupy the same region of space simultaneously, passing like ships in the night along their respective cosmic highways. Gravitational perturbations from encounters with Earth and other planets gradually modify the asteroid's orbit over periods of thousands or millions of years. Each close approach, while not resulting in collision, produces subtle changes in orbital velocity that accumulate into significant alterations of trajectory over time. Computer simulations that integrate these gravitational effects forward through millions of years reveal a chaotic evolution of the orbit, with periods of relative stability punctuated by dramatic changes caused by particularly close planetary encounters. The Yarkovsky effect contributes additional orbital evolution through the asymmetric emission of thermal radiation from the asteroid's rotating surface. As the object spins, its sun-facing hemisphere absorbs solar energy and heats up, then re-radiates this energy as infrared light several hours later when rotation carries the heated region into shadow. This thermal emission creates a small net force that acts like a weak rocket engine, gradually changing the asteroid's orbital velocity by microscopic amounts that nevertheless accumulate into measurable orbital changes over geological timescales. Seasonal variations in solar heating occur as the asteroid's elliptical orbit carries it closer to and farther from the Sun during its orbital cycle. At perihelion, the point of closest approach to our parent star, temperatures on the sunlit surface may exceed several hundred degrees Celsius, hot enough to cause thermal expansion and stress fracturing of the rocky surface materials. At aphelion, the most distant point of the orbit, surface temperatures drop well below the freezing point of water, creating thermal contraction that opens new cracks and gradually weakens the asteroid's structural integrity. The surface geology of the asteroid remains largely hidden from direct observation due to its small size and enormous distance from Earth. Radar observations from powerful planetary radar systems can detect its overall shape and rotation characteristics, while infrared observations provide estimates of surface temperature and thermal properties. These remote sensing techniques suggest a surface covered with a layer of fine dust and small fragments called regolith, created by billions of years of micrometeorite impacts that gradually pulverize exposed rock into increasingly smaller particles. Despite its designation as potentially hazardous, statistical analysis of the asteroid's orbital evolution indicates an extremely low probability of Earth impact over the next several centuries. Monte Carlo simulations that account for uncertainties in orbital determination and gravitational perturbations suggest odds of collision on the order of 1 in several million during the next 1,000 years. These calculations provide reassurance that immediate defensive action remains unnecessary, though continued observation and orbit refinement help improve the accuracy of long-term risk assessments. The asteroid serves as a time capsule, preserving materials from the early solar system in a nearly pristine state. Unlike Earth, where geological processes have recycled and altered most primordial materials, small asteroids lack sufficient internal heat to drive chemical differentiation or surface renewal. Their compositions retain chemical and isotopic signatures from the epoch of planetary formation, making them valuable scientific targets for understanding the conditions and processes that created the solar system's rocky planets. Space missions to similar near-Earth asteroids have revealed unexpected complexities in their physical properties and surface characteristics. The near-Shoemaker mission to asteroid Eros discovered a heavily cratered surface covered with impact debris, while the Hayabusa missions to asteroids Itokawa and Ryugu found rubble pile structures held together primarily by weak gravitational attraction rather than structural strength. These discoveries challenge traditional assumptions about asteroid properties and complicate efforts to predict how such objects might respond to potential deflection attempts. The gentle cosmic irony of this particular asteroid lies in its simultaneous proximity and remoteness from human civilization. Classified as a near-Earth object and tracked by multiple observatories worldwide, it nonetheless remains farther away than any human has ever traveled. Beyond the reach of current propulsion technology for crewed missions, its closest approaches to Earth occur at distances roughly 5 times greater than that of the Moon, close enough to be considered threatening by astronomical standards, yet impossibly distant by terrestrial measures. International space agencies have identified similar near-Earth asteroids as potential targets for future robotic missions that could test planetary defense technologies while advancing scientific understanding of these primitive solar system remnants. Kinetic impact missions like NASA's successful DART experiment demonstrate humanity's growing capability to alter asteroid trajectories through carefully planned collisions, while sample return missions provide detailed compositional analysis of asteroid materials in terrestrial laboratories. As the asteroid continues its ancient journey through the inner solar system, it maintains its patient orbit regardless of human attention or concern. The mathematical precision of celestial mechanics ensures that its future path can be predicted with remarkable accuracy for decades or centuries ahead, while the fundamental limitations of chaos theory guarantee that its ultimate fate remains unknowable across the vast timescales of astronomical evolution. For now, it simply continues its billion-year-old dance around the Sun, one small participant in the complex gravitational ballet that governs the motion of all solar system objects. The Torino Impact Hazard Scale displays its numerical hierarchy with the dispassionate precision of a scientific instrument designed to quantify cosmic risk. From 0 to 10, each level represents an increasingly urgent assessment of asteroid threat potential. Though the vast majority of newly discovered near-Earth objects earn the reassuring designation of 0, indicating no cause for public concern. The scale, developed by MIT planetary scientist Richard Binzel and formally adopted by the International Astronomical Union in 1999, attempts to translate the complex mathematics of orbital mechanics into categories that both scientists and the public can readily understand. 0 dominates the statistical landscape of asteroid risk assessment, encompassing objects whose collision probability falls below 1 in 10 million, or whose predicted impact energy would prove insufficient to cause significant regional damage. Most asteroids smaller than 50 meters across automatically receive this classification, as atmospheric entry typically destroys such objects before they reach Earth's surface. The gentle irony of the Torino scale lies in its implicit acknowledgement that 0 represents not the absence of risk, but rather risk so negligible that it falls below the threshold of practical concern for human civilization. Category 1. Objects merit attention from astronomers but require no public alarm, representing asteroids with slightly higher collision probabilities or marginally larger sizes that warrant continued observation and orbit refinement. These discoveries undergo more frequent telescopic monitoring to improve orbital calculations and reduce uncertainty in long-term trajectory predictions. Most objects initially assigned to Category 1 eventually migrate to Category 0 as additional observations provide more precise orbital determinations and reveal that collision probabilities were overestimated due to limited initial data. The middle ranges of the Torino scale levels 2 through 4 describe objects that deserve increasingly close attention from the international asteroid tracking community. Category 2 asteroids merit concern from astronomers and careful monitoring by governmental space agencies, while Category 3 objects warrant attention from government planning agencies responsible for emergency preparedness and civil defense. Category 4 represents a close encounter likely to cause regional devastation that merits contingency planning by national governments, though the probability of impact typically remains low enough that public alarm would be premature. Categories 5 through 7 describe objects with increasingly certain prospects for Earth impact and correspondingly greater predicted damage levels. A Category 5 asteroid poses a serious but still uncertain threat of regional devastation, while Category 6 indicates a close encounter with a large object that poses an unusual level of concern, regardless of impact probability. Category 7 represents an object certain to cause unprecedented regional devastation, meriting international attention and detailed contingency planning by affected nations and international organizations. The upper reaches of the Torino scale levels 8, 9, and 10 describe scenarios that transition from regional concerns to threats against global civilization itself. Category 8. Asteroids are certain to cause regional devastation, but uncertain to cause global climatic catastrophe. While Category 9 objects are certain to cause unprecedented global climatic catastrophe that threatens the future of civilization, Category 10, the scale's maximum level, indicates certain collision with an object large enough to cause a global climatic catastrophe capable of threatening the survival of life on Earth as we know it. No asteroid has ever been assigned a Torino scale rating higher than 4, and most objects that initially receive elevated ratings are subsequently downgraded to lower categories as improved orbital calculations reduce impact probabilities or reveal that closest approach distances were initially underestimated. The asteroid 999942 Apophis briefly achieved a Category 4 rating when first discovered in 2004, but additional observations and radar measurements eventually reduced its impact probability to essentially 0, earning it a permanent Category 0 classification. The European Space Agency operates a complementary risk assessment system called the Palermo Technical Impact Hazard Scale, which provides more nuanced risk evaluation for scientific and technical audiences. Unlike the Torino scale's discrete categories, the Palermo scale uses a continuous logarithmic progression that accounts for both impact probability and the background risk posed by all asteroids of similar size. This technical approach allows more precise comparison between different objects and provides better guidance for prioritizing observational resources and potential deflection missions. Risk assessment calculations must account for numerous sources of uncertainty that can dramatically affect long-term impact predictions. Observational errors in position measurements, uncertainties in asteroid physical properties, imperfect knowledge of gravitational perturbations, and chaotic orbital evolution all contribute to probability distributions that broaden significantly when projected far into the future. An asteroid's impact risk often proves highest immediately after discovery, when orbital uncertainties are largest, then decreases as additional observations refine trajectory calculations. The temporal dimension of asteroid risk assessment presents unique challenges for both scientific analysis and policy planning. Objects with significant impact probabilities occurring decades or centuries in the future raise questions about appropriate response timelines and the allocation of current resources to address distant potential threats. The typical human planning horizon of years or decades conflicts with the astronomical timescales over which asteroid risks evolve, creating tensions between immediate practical concerns and long-term civilizational security. Statistical analysis of the entire near-Earth asteroid population provides context for individual risk assessments by establishing baseline expectation rates for impacts of various sizes and energies. Large impacts capable of causing global climatic effects occur on average every few 100,000 to several million years, while smaller impacts that could destroy cities or cause significant regional damage happen much more frequently. This statistical background helps calibrate the significance of specific threats identified through telescopic surveys. The Torino scale deliberately avoids specifying detailed damage scenarios for different impact energies, recognizing that actual consequences depend heavily on impact location, local population density, and numerous other factors that cannot be predicted in advance. An asteroid impact in a remote ocean area might cause minimal direct damage despite releasing enormous amounts of energy, while a much smaller object striking a densely populated metropolitan area could cause catastrophic casualties and economic disruption far exceeding its raw energy yield. Cultural and psychological factors influence public perception of asteroid risks in ways that often diverge significantly from scientific risk assessments. The dramatic nature of potential impact scenarios, combined with their portrayal in popular entertainment, can create public anxiety levels that exceed what statistical analysis would suggest is appropriate. Conversely, the extreme rarity of significant impacts and the abstract nature of long-term probabilities may lead to insufficient concern about risks that scientists consider worthy of serious attention and resources. International cooperation in asteroid risk assessment faces challenges related to data sharing, resource allocation, and coordinated response planning across national boundaries. While the scientific community maintains strong collaborative relationships for sharing observations and orbital calculations, the development of planetary defense capabilities involves military and national security considerations that complicate international coordination. The global nature of asteroid threats necessitates international cooperation, yet the technological capabilities required for effective planetary defense remain concentrated in a small number of spacefaring nations. The establishment of formal risk assessment protocols represents a relatively recent development in humanity's relationship with cosmic hazards. For most of human history, asteroid impacts remained unpredictable natural disasters beyond the scope of scientific understanding or technological mitigation. Only within the past few decades have telescopic surveys and computational capabilities advanced sufficiently to provide meaningful warning times and risk quantification for potential future impacts, transforming asteroid threats from acts of cosmic fate into manageable technological challenges. The Torino scale continues to evolve as scientists gain experience with asteroid risk assessment and public communication about cosmic hazards. Proposed revisions consider modifications to category definitions, additional factors in risk evaluation, and improved methods for communicating uncertainty and temporal aspects of impact predictions. These refinements reflect growing sophistication in both the scientific understanding of asteroid populations and the practical challenges of translating technical risk assessments into actionable information for policymakers and the public. Radio waves stretch across the void between Earth and asteroid, traveling at the speed of light through nearly empty space until they encounter the ancient rocky surface that has been wandering the solar system since its formation billions of years ago. The Goldstone Deep Space Communications Complex in California's Mojave Desert transmits these radar pulses with precisely controlled timing, each burst containing millions of watts of radio energy focused into a narrow beam aimed at coordinates calculated from optical observations. The electromagnetic radiation crosses the gulf of interplanetary space in minutes or hours, depending on the asteroid's distance, carrying with it the potential to reveal secrets about the object's size, shape, rotation, and surface characteristics that remain invisible to conventional telescopes. When the radar pulse encounters the asteroid's surface, the interaction between radio waves and rocky material creates a complex pattern of reflection and scattering that depends on numerous physical properties of the target object. Smooth. Flat surfaces reflect radio energy in predictable directions according to the laws of geometric optics, while rough, irregular terrain scatters the signal in multiple directions like light bouncing off a gravel road. The asteroid's rotation causes different surface features to move in and out of view, creating subtle variations in the strength and characteristics of the reflected signal that trained analysts can interpret to reconstruct the object's three-dimensional shape and spin characteristics. The return journey of the reflected radar signal carries a wealth of encoded information about the asteroid's physical properties. Variations in signal strength reveal the distribution of surface roughness across different regions of the object, while subtle frequency shifts caused by the Doppler effect provide precise measurements of rotational velocity and the motion of individual surface features. The time delay between transmission and reception, measured with atomic clock precision, yields distance measurements accurate to within a few meters across millions of miles of space, far exceeding the positional accuracy achievable through optical observations alone. Planetary radar systems like those at Goldstone and the Arecibo Observatory transform these reflected signals into detailed images that reveal asteroid surface features invisible to even the most powerful optical telescopes. The resolution of radar imaging depends on both the power of the transmitted signal and the duration of the observation campaign, with extended monitoring sessions capable of producing maps showing features as small as a few meters across on nearby asteroids. These radar images often reveal unexpected surface characteristics, impact craters, ridges, valleys, and boulder fields that tell the story of each asteroid's individual history of collisions and gravitational interactions. The radar technique proves particularly valuable for determining asteroid rotation characteristics, which remain difficult to measure through optical methods alone. Most asteroids exhibit complex tumbling motions rather than simple rotation around a single axis, the result of asymmetric gravitational torques and collision impacts accumulated over geological timescales. Radar observations can detect these subtle variations in rotational motion and reconstruct the complete orientation dynamics of the asteroid. Information essential for understanding how thermal forces, like the Yarkovsky effect, influence long-term orbital evolution. Binary asteroid systems reveal themselves through distinctive radar signatures that distinguish them from single objects of similar size and brightness. When radar waves illuminate a binary system, the signals reflected from the primary and secondary components arrive at Earth with slightly different time delays and Doppler shifts, creating characteristic patterns in the received data. Analysis of these radar echoes can determine the orbital period of the binary system, the size ratio between the two components, and sometimes even the detailed shapes of both objects independently. The surface composition of asteroids influences their radar reflectivity in ways that complement information obtained through infrared and visible light spectroscopy. Metallic asteroids, composed primarily of iron and nickel, reflect radar signals much more efficiently than rocky objects of similar size, allowing radar observers to estimate the metal content of asteroid surfaces. This capability proves especially valuable for identifying potentially valuable targets for future asteroid mining operations. As metallic asteroids contain concentrated deposits of platinum group elements and other rare metals that command high prices in terrestrial markets, thermal properties of asteroid surfaces become apparent through radar observations conducted at different wavelengths and power levels. The penetration depth of radar signals depends on the radio frequency used, with longer wavelengths capable of probing several meters below the surface, while shorter wavelengths remain sensitive primarily to surface conditions. These multi-wavelength radar studies reveal information about subsurface structure, porosity, and the thickness of the regolith layer that covers most asteroid surfaces as a result of billions of years of micrometeorite bombardment. The irregular shapes revealed by radar imaging challenge traditional assumptions about asteroid structure and formation mechanisms. Many asteroids exhibit highly elongated or contact binary configurations that suggest formation through low-velocity collisions between separate objects rather than gravitational accretion of smaller particles. Some asteroids display evidence of catastrophic disruption and subsequent gravitational reaccumulation, creating rubble pile structures with very low bulk densities and complex internal architectures that would be impossible to detect through optical observations alone. Radar observations contribute essential data for planetary defense calculations by providing precise measurements of asteroid size, mass, and structural properties that influence how objects might respond to potential deflection attempts. The effectiveness of kinetic impact emissions depends heavily on the target asteroid's internal structure, with solid, monolithic objects responding differently to high-velocity collisions than loosely bound rubble piles. Radar-derived knowledge of asteroid physical properties allows mission planners to optimize spacecraft designs and impact strategies for maximum deflection efficiency. The technological requirements for planetary radar observations push the boundaries of radio astronomy, instrumentation, and signal processing capabilities. Detecting the extremely weak radar echoes from small, distant asteroids requires transmitters capable of generating megawatts of radio power and receivers sensitive enough to measure signals billions of times weaker than the original transmission. The Earth's rotation and orbital motion, combined with the asteroid's own movement through space, create complex Doppler shifts that must be compensated through sophisticated signal processing algorithms. Atmospheric effects limit the effectiveness of ground-based radar systems, particularly at higher radio frequencies where water vapor and other atmospheric constituents absorb or scatter transmitted signals. The ionosphere, a layer of charged particles in Earth's upper atmosphere, can reflect or refract radio waves in ways that distort radar observations of space targets. These atmospheric limitations have motivated proposals for space-based planetary radar systems that could operate without interference from Earth's atmospheric envelope. International cooperation in planetary radar observations involves coordination between multiple facilities to maximize sky coverage and observing time for the highest priority asteroid targets. The loss of the Arecibo Observatory's primary dish in 2020 reduced global planetary radar capability significantly. Concentrating most radar asteroid observations at the Goldstone facility and emphasizing the need for additional radar systems to maintain comprehensive monitoring of near-Earth objects. Proposed future radar systems in both hemispheres would restore and expand humanity's capability to characterize potentially hazardous asteroids through radio observations. The gentle paradox of planetary radar lies in its use of terrestrial radio technology to probe objects that formed in the earliest epochs of solar system history, long before electromagnetic radiation existed anywhere except in the hearts of stars. These ancient wanderers, composed of materials that condensed from the primordial solar nebula, now find themselves illuminated by artificial radio beams that reveal their secrets to human observers across the vast emptiness of interplanetary space. Each radar echo carries information that has been locked within rocky surfaces for billions of years, waiting for this technological moment when human curiosity and capability finally intersect with cosmic accessibility. The radar waves continue their journey back toward Earth, carrying with them the encoded signatures of asteroid surface roughness, internal structure, and rotational dynamics. Within hours, this information will be decoded by computer algorithms and transformed into scientific knowledge that advances humanity's understanding of both individual asteroids and the broader population of objects that share our cosmic neighborhood. The invisible conversation between Earth and asteroid, conducted in the universal language of electromagnetic radiation, adds another layer to our species' gradually expanding awareness of the solar system's hidden complexities. The Space Guard survey unfolds as humanity's most systematic attempt to catalog the cosmic neighborhood, a methodical census aimed at discovering 90% of all near-Earth asteroids larger than 1 kilometer in diameter. This ambitious goal, established by the United States Congress in 1998 and embraced by the international astronomical community, represents a fundamental shift from reactive to proactive planetary defense strategy. Rather than waiting for potentially hazardous objects to reveal themselves through chance encounters or catastrophic impacts, the survey deliberately seeks them out through coordinated telescopic observations that span decades of patient, systematic sky coverage. The 1 kilometer threshold reflects careful analysis of impact consequences and detection capabilities, representing objects large enough to cause regional or global catastrophic damage while remaining within the sensitivity limits of ground-based telescopic surveys. Asteroids of this size carry kinetic energies equivalent to millions of nuclear weapons, sufficient to devastate areas the size of small nations and potentially trigger climate disruption through dust injection into the stratosphere. Yet their thermal emission and reflected sunlight make them detectable by existing telescope systems at distances of millions of miles, providing warning times measured in years or decades rather than days or hours. Statistical models of the near-Earth asteroid population suggest that approximately 1,000 objects larger than 1 kilometer exist in Earth-crossing orbits, based on extrapolations from discovery rates, orbital dynamics simulations, and crater chronology studies of planetary surfaces throughout the solar system. Current catalogs contain more than 90% of these large objects, indicating that the Space Guard survey's primary objective has been largely achieved through the combined efforts of multiple survey programs operating around the globe. This success represents one of the most complete censuses of any natural hazard threat that humanity has ever undertaken. The survey's methodology relies on systematic coverage of the entire accessible sky over periods of months or years, with particular attention to regions where near-Earth asteroids are most likely to be discovered, opposition regions, where objects appear at their brightest due to favorable illumination geometry, receive priority in observing schedules, as do areas of sky where asteroid orbital dynamics concentrate potentially hazardous objects. Survey telescopes revisit the same sky regions repeatedly to catch objects that may have been too faint to detect during previous observations or that have moved into more favorable positions. Automated detection systems process millions of astronomical images each year, searching for the subtle motion signatures that distinguish asteroids from background stars and galaxies. Modern pattern recognition algorithms, trained on databases containing hundreds of thousands of previously confirmed asteroid detections, achieve detection rates and false positive rejection capabilities that far exceed human visual inspection methods. These systems operate continuously during clear nights, processing each evening's observations and flagging potential asteroid candidates for follow-up observation and orbital analysis. The survey extends beyond simple detection to include detailed characterization of discovered objects through multi-wavelength photometry, spectroscopy, and radar observations when possible. Size estimates derived from thermal infrared observations complement visible light brightness measurements to determine asteroid diameters and surface reflectivity characteristics. Spectroscopic observations reveal surface composition and mineralogy, while radar measurements provide precise size, shape, and rotation information for objects that approach within radar range of Earth. International coordination ensures that the Space Guard survey represents a truly global effort rather than the isolated work of individual national space agencies. The Minor Planet Center serves as the central repository for all asteroid observations worldwide, maintaining standardized databases and communication protocols that allow astronomers from different countries and institutions to contribute observations and access the accumulated knowledge of the entire international community. This cooperative approach maximizes the scientific return on investment while minimizing duplication of effort across multiple survey programs. The survey's success in achieving its primary goal has revealed the need for expanded objectives that address smaller but still potentially dangerous asteroids. Congressional authorization in 2005 established a new target of detecting 90% of near-Earth objects larger than 140 meters in diameter, extending the survey mandate to include objects capable of causing significant regional damage even if they lack global impact potential. This expanded mission requires more sensitive telescopes and longer survey durations, as smaller asteroids prove much more difficult to detect and track reliably. Detection statistics reveal interesting patterns in the size distribution and orbital characteristics of the near-Earth asteroid population. Large asteroids prove relatively rare, but are concentrated in orbital families that suggest common origins from catastrophic disruption events in the main asteroid belt. Smaller objects exhibit more diverse orbital characteristics and appear to represent a steady influx from multiple source regions throughout the solar system. These patterns provide insights into the dynamical processes that transport asteroids from their formation locations into Earth-crossing orbits. The temporal evolution of survey capabilities demonstrates the exponential improvement in astronomical instrumentation and data processing over the past several decades. Early asteroid discoveries required photographic plates and human visual examination, limiting discovery rates to a few dozen objects per year. Modern CCD-based surveys equipped with automated detection software routinely discover thousands of new asteroids annually, with individual facilities sometimes cataloging more objects in a single night than were known throughout all of human history just a few decades ago. Survey completeness varies significantly with asteroid size, orbital characteristics, and observational circumstances. While the catalog of kilometer-sized near-Earth asteroids approaches statistical completeness, smaller objects remain severely underrepresented in current databases. Objects in certain orbital configurations, such as those that approach Earth primarily during daylight hours or spend most of their time in the outer solar system, prove particularly challenging to detect and may remain undiscovered for extended periods despite their potential hazard status. The economic costs of comprehensive asteroid surveys remain modest compared to other natural disaster mitigation programs. Yet, the potential benefits in terms of avoided catastrophic damage justify continued expansion of survey capabilities. Ground-based telescopic surveys operate on budgets measured in tens of millions of dollars annually, while space-based infrared surveys like NEOS add comparable costs but provide unique capabilities for detecting dark, low-reflectivity asteroids that remain invisible to optical surveys. These investments purchase humanity's first comprehensive situational awareness of cosmic impact hazards. Future survey technologies promise to accelerate discovery rates while extending detection capabilities to smaller and more distant objects. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire southern sky repeatedly with unprecedented sensitivity, potentially doubling or tripling current asteroid discovery rates when it begins operations. Space-based survey missions like NEOCAM could detect asteroids throughout the inner solar system without atmospheric interference, providing complementary coverage to ground-based facilities. The philosophical implications of the SpaceGuard survey extend beyond practical planetary defense considerations to encompass humanity's evolving relationship with cosmic hazards. For the first time in our species' history, we possess both the technological capability to detect approaching threats and the potential means to mitigate them through spacecraft missions designed to alter asteroid trajectories. This transition from passive vulnerability to active planetary defense represents a fundamental milestone in the development of technological civilization. The survey continues its patient work each clear night, adding new discoveries to humanity's growing catalog of cosmic neighbors while refining the orbits and characteristics of previously known objects. Automated telescopes scan predetermined sky coordinates with mechanical precision, their electronic detectors recording the faint light that has traveled across millions of miles of empty space to reach Earth. Each photon carries information about objects that formed during the solar system's birth, now serving as both potential threats and valuable scientific resources for future generations. The gentle irony of asteroid surveying lies in its transformation of cosmic threats into manageable statistical problems through the application of systematic observation and mathematical analysis. Objects that once represented unpredictable acts of celestial catastrophe now appear in computer databases with precisely calculated orbits, estimated sizes, and quantified impact probabilities. The universe's capacity for surprise remains unchanged, but humanity's ability to anticipate and prepare for cosmic encounters continues to expand with each night's observations. Orbital resonances weave invisible threads through the architecture of the solar system, creating zones where Jupiter's immense gravitational influence transforms the stable circular paths of main belt asteroids into increasingly eccentric ellipses that eventually cross Earth's orbital territory. These resonant regions, named after the mathematical ratios that describe their relationship to Jupiter's 12-year orbital period, act as cosmic conveyor belts that steadily transport rocky debris from the asteroid belt into the inner solar system over timescales measured in millions of years. The 3-1 resonance, located approximately 2.5 astronomical units from the Sun, represents one of the most significant sources of near-Earth asteroids. Objects trapped in this resonance complete exactly 3 orbits around the Sun for every one of Jupiter's, creating a synchronized gravitational dance that repeats with clockwork precision every few years. During each alignment, Jupiter's gravity delivers a small but persistent kick to asteroids in resonant orbits, gradually increasing their orbital eccentricity until their paths stretch far enough inward to intersect the orbits of Mars and Earth. The physical mechanism of resonant transport operates through a process that celestial mechanicians call chaotic diffusion, where tiny gravitational perturbations accumulate over vast periods of time to produce dramatic changes in orbital configuration. An asteroid that begins its journey in a nearly circular orbit within the main belt experiences periodic gravitational nudges from Jupiter that slowly pump up its orbital eccentricity. The process unfolds imperceptibly at first, with changes in orbital shape too small to measure over human timescales, yet inexorably effective over the millions of orbital cycles that comprise astronomical time. Mathematical analysis reveals that resonant zones within the asteroid belt correspond precisely to gaps in the distribution of stable orbits. Regions where few asteroids survive for extended periods due to the disruptive influence of Jovian gravity. The Kirkwood gaps, named after 19th century American astronomer Daniel Kirkwood, who first recognized their significance, mark the locations of major resonances where Jupiter's gravitational influence proves too strong to permit long-term orbital stability. These empty zones serve as transit corridors through which asteroids migrate from the outer belt toward Earth-crossing trajectories. The journey from main belt to near-Earth orbit typically requires several million years of gradual orbital evolution, during which asteroids experience multiple close encounters with Mars and occasional interactions with Earth's gravitational field. Each planetary encounter modifies the asteroid's trajectory unpredictably, sometimes accelerating the migration towards smaller, more eccentric orbits, and sometimes ejecting objects entirely from the inner solar system. Statistical models suggest that only a small fraction of asteroids entering resonant transport survive the complete journey to become observable near-Earth objects. Computer simulations that integrate the orbital evolution of test particles through resonant zones reveal the chaotic nature of this transport process. Initially, identical orbits diverge exponentially over time due to the sensitive dependence on initial conditions that characterizes all chaotic dynamical systems. An asteroid's ultimate fate, whether it becomes a near-Earth object, collides with a planet, or gets ejected from the solar system entirely, depends on subtle details of its initial orbital elements that cannot be predicted in advance, even with perfect knowledge of gravitational forces. The Yarkovsky effect compounds the complexity of resonant transport by introducing thermal forces that depend on asteroid physical properties rather than purely gravitational dynamics. Small asteroids experience larger thermal perturbations relative to their masses, causing them to migrate through resonant zones more rapidly than larger objects. This size-dependent transport mechanism helps explain the observed size distribution of near-Earth asteroids, which differs significantly from the population that remains in stable main belt orbits. Observational evidence for resonant transport comes from multiple sources of astronomical data that independently support theoretical predictions about asteroid orbital evolution. Spectroscopic studies reveal compositional similarities between certain near-Earth asteroids and main belt asteroids located near resonant boundaries, suggesting genetic relationships that support the transport hypothesis. Meteorite specimens that reach Earth's surface often exhibit cosmic ray exposure, ages consistent with multi-million-year journeys through interplanetary space, matching theoretical predictions for resonant migration timescales. The N6 secular resonance adds another layer of complexity to asteroid orbital evolution by introducing precession effects that can destabilize orbits even outside the major mean motion resonances. This gravitational phenomenon causes the orientation of asteroid orbits to precess at rates that sometimes match the precession of planetary orbits, creating periodic alignments that pump up orbital eccentricity through subtle but persistent gravitational coupling. Objects affected by secular resonances may experience rapid orbital changes that transport them into Earth-crossing trajectories within hundreds of thousands rather than millions of years. Jupiter's role as the solar system's primary architect of asteroid orbits extends beyond simple gravitational perturbations to include its influence on the collisional evolution of the main asteroid belt. The giant planet's gravity affects the relative velocities at which asteroids encounter each other during collisions, influencing both the frequency and outcomes of these impacts. Higher collision velocities, induced by Jovian gravitational stirring, tend to produce more catastrophic disruptions that create families of fragments with similar orbital characteristics and compositions. The steady influx of asteroids from resonant transport provides a continuous supply of fresh material to the near-Earth environment, replacing objects that are gradually removed through planetary collisions or gravitational ejection from the inner solar system. Without this ongoing replenishment from main belt sources, the population of near-Earth asteroids would decay to negligible levels within a few million years due to natural loss processes. The observed abundance of near-Earth objects therefore provides direct evidence for the effectiveness of resonant transport mechanisms. Gravitational interactions with Earth during close approaches can dramatically accelerate the final stages of orbital evolution for asteroids that have migrated from the main belt through resonant zones. The Opic-Arnold theory describes how planetary encounters scatter asteroid orbits into new configurations that may either increase or decrease collision probabilities with Earth. Some close approaches deflect asteroids onto safer trajectories that carry them away from Earth's orbital vicinity, while others nudge objects onto more dangerous paths that increase future impact risks. The temporal variability of resonant transport introduces long-term fluctuations in the supply rate of new near-Earth asteroids, with periods of enhanced migration alternating with epochs of reduced activity. These variations result from changes in the dynamical structure of resonant zones caused by the gradual evolution of planetary orbits over astronomical timescales. The orbits of Jupiter and the other giant planets change slowly due to their mutual gravitational interactions, subtly altering the locations and strengths of resonances throughout the asteroid belt. Modern numerical integration techniques allow astronomers to trace the orbital evolution of individual asteroids backward through time to identify their probable source regions within the main belt. These computational archaeology studies reveal that different spectroscopic classes of near-Earth asteroids originate from distinct zones within the asteroid belt, with S-type objects typically arriving from the inner belt, while C-type asteroids more commonly originate from outer belt locations. This information provides insights into the compositional structure of the original solar nebula from which all solar system objects formed. The discovery of asteroid pairs and clusters with nearly identical orbits provides additional evidence for recent disruption events that create multiple fragments following similar trajectories toward Earth-crossing orbits. These young asteroid families, identified through careful analysis of orbital elements and physical properties, offer opportunities to study the immediate aftermath of catastrophic collisions and the initial stages of resonant transport. Some pairs may represent binary asteroids that have recently separated due to rotational instability or tidal disruption during close planetary encounters. The gentle cosmic irony of resonant transport lies in Jupiter's dual role as both protector and threatener of Earth's biosphere. While the giant planet's gravity shields the inner solar system from most long-period comets originating in the outer reaches of the solar system, it simultaneously pumps a steady stream of potentially hazardous asteroids inward from the main belt. The same gravitational influence that may have enabled the development of complex life on Earth by reducing the flux of large impacts also ensures a continuing supply of smaller but still dangerous objects that require ongoing monitoring and potential mitigation efforts. NEOWISE drifts through the vacuum of space at an altitude of 525 kilometers above Earth's surface, its cryogenically cooled infrared telescope scanning the sky with sensors designed to detect the gentle thermal glow of asteroids, invisible to ground-based optical surveys. Originally launched as the Wide-Field Infrared Survey Explorer in 2009, the spacecraft began its extended mission as the Near-Earth Object Wide-Field Infrared Survey Explorer after depleting its primary coolant supply, continuing its systematic infrared survey with reduced but still remarkable sensitivity to asteroid thermal emission. The spacecraft's infrared vision reveals asteroids through their heat signatures rather than reflected sunlight, providing a fundamentally different perspective on the near-Earth object population than traditional optical surveys can achieve. Dark asteroids that reflect only a few % of incident sunlight remain nearly invisible to conventional telescopes, yet their surfaces radiate infrared energy at wavelengths where NEOWISE's detectors achieve peak sensitivity. This thermal detection capability proves especially valuable for discovering the most potentially dangerous asteroids, those with dark, carbon-rich surfaces that absorb solar energy efficiently while reflecting very little visible light back toward Earth. The physics of asteroid thermal emission follows the Stefan Boltzmann law, which relates the total energy radiated by a black body to the fourth power of its surface temperature. Asteroids closer to the Sun receive more intense solar radiation and reach higher equilibrium temperatures, making them brighter in infrared wavelengths despite their distance from Earth. Objects in the outer regions of their orbits appear cooler and dimmer in thermal infrared. Yet NEOWISE's sensitive detectors can still measure their heat signatures across millions of miles of interplanetary space. Simultaneous detection at multiple infrared wavelengths allows NEOWISE to determine both the size and albedo of discovered asteroids through thermal modeling techniques. The ratio of thermal emission at different wavelengths provides information about surface temperature, while the absolute brightness in infrared bands indicates the total amount of energy being radiated. Combined with distance measurements derived from orbital calculations, these observations yield accurate estimates of asteroid diameters and surface reflectivity that complement but often prove more reliable than optical photometry alone. The thermal inertia of asteroid surfaces introduces subtle but measurable effects in infrared observations that provide insights into surface texture and composition. Objects covered with fine dust or regolith respond rapidly to changes in solar illumination, heating up quickly when exposed to sunlight and cooling efficiently when shadowed. Solid rocky surfaces with higher thermal inertia store heat more effectively and exhibit smaller temperature variations throughout their rotational cycles, creating distinctive thermal signatures that trained analysts can interpret to infer surface properties. NEOWISE's orbital mechanics create a unique observational geometry that complements ground-based surveys by accessing different regions of sky and providing different illumination conditions for asteroid detection. The spacecraft's sun-synchronous polar orbit allows it to observe objects at solar elongation angles that remain inaccessible to terrestrial telescopes, while its position outside Earth's atmosphere eliminates atmospheric absorption that limits ground-based infrared observations. This space-based perspective proves especially valuable for detecting asteroids with orbits that carry them primarily in the direction of the Sun as seen from Earth. The mission's systematic survey strategy divides the sky into overlapping coverage zones that receive repeated observations over periods of days or weeks, allowing for the confirmation of moving objects and the measurement of thermal variability caused by asteroid rotation. Each region of sky typically receives 6 or more independent observations, spaced over intervals ranging from hours to several days, providing sufficient temporal baseline to distinguish genuine asteroid detections from instrumental noise or background sources like distant galaxies and stars. Data processing algorithms developed specifically for NEOWISE observations must account for the complex thermal behavior of rotating asteroids, whose surfaces experience periodic heating and cooling cycles. Advanced thermal models incorporate factors such as surface roughness, thermal conductivity, and the effects of shadowing by topographic features to predict how asteroid temperatures vary with rotation phase and orbital position. These sophisticated analyses can sometimes detect thermal signatures of surface features, like large craters or boulder fields that remain invisible to optical observations. The spacecraft's infrared detectors operate at wavelengths where zodiacal dust microscopic particles distributed throughout the inner solar system, creates a diffuse background glow that can interfere with asteroid detection. Careful subtraction of this zodiacal light background requires precise calibration and modeling of both the instrumental response and the three-dimensional distribution of interplanetary dust. The same dust particles that complicate asteroid observations also provide valuable scientific information about the evolution and dynamics of small bodies throughout the solar system. CNEOS has discovered thousands of previously unknown near-Earth asteroids since beginning its extended mission, with discoveries continuing at a steady pace as the spacecraft systematically surveys the accessible portions of the sky. Many of these infrared-detected objects remained completely unknown to optical surveys despite decades of systematic ground-based searching, demonstrating the complementary nature of thermal and optical detection techniques. The mission's most significant discoveries include several potentially hazardous asteroids larger than 1 kilometer in diameter that had escaped detection by previous surveys. The spacecraft's ability to measure accurate asteroid diameters has revolutionized understanding of the size distribution and impact hazard assessment for the near-Earth object population. Previous optical surveys often overestimated the sizes of dark asteroids while underestimating the sizes of highly reflective objects, leading to systematic errors in hazard evaluation. CNEOS's thermal measurements provide unbiased size estimates that allow more accurate assessment of impact energies and damage potential for individual objects. Thermal phase curves measured by repeated CNEOS observations of the same asteroids provide information about surface thermal properties, rotation periods, and pole orientations that prove difficult to obtain through other observational techniques. These thermal light curves complement optical photometry and radar observations to build comprehensive physical models of individual asteroids, improving predictions of how such objects might respond to potential deflection attempts and enhancing scientific understanding of their internal structure and composition. The mission's longevity has enabled the measurement of thermal property variations among different asteroid spectral classes, revealing systematic differences in surface characteristics between various taxonomic groups. S-type asteroids typically exhibit thermal properties consistent with rocky compositions and moderate thermal inertia, while C-type objects often display characteristics suggesting surfaces covered with fine-grained, low thermal inertia regolith. These thermal measurements provide ground truth for theoretical models of asteroid surface evolution and collisional processing. CNEOS observations contribute to planetary defense efforts by providing accurate size measurements for potentially hazardous asteroids, information essential for evaluating deflection mission requirements and assessing potential impact consequences. The energy required to alter an asteroid's trajectory scales with the object's mass, which depends on both size and bulk density. Precise diameter measurements from thermal infrared observations reduce uncertainties in mass estimates and enable more accurate planning for potential mitigation missions. The spacecraft's infrared survey capabilities extend beyond simple asteroid detection to include characterization of comet activity through measurement of thermal emission from dust particles ejected by sublimating volatile materials. CNEOS has observed numerous comets during their approaches to the inner solar system, providing insights into the thermal behavior of cometary nuclei and the evolution of dust production as these objects warm under increasing solar radiation. These observations help distinguish between asteroids and dormant or weakly active comets that might otherwise appear similar in optical surveys. Future infrared space missions designed to continue and expand upon CNEOS's asteroid survey capabilities face technical challenges related to detector sensitivity, thermal background subtraction, and survey efficiency. Proposed missions like NEOCAM would incorporate larger telescopes and more sensitive infrared detectors to push thermal asteroid detection to smaller sizes and greater distances, potentially discovering tens of thousands of additional near-Earth objects over multi-year survey operations. The gentle irony of infrared asteroid detection lies in its reliance on solar energy absorbed and re-radiated by objects that formed in the cold outer regions of the early solar nebula. These ancient fragments of planetary formation now serve as cosmic heat sources, their thermal glow providing the electromagnetic signatures that reveal their presence to human instruments across the vast emptiness of interplanetary space. Each infrared photon detected by NEOWISE carries information about surface temperatures, thermal properties, and energy balance that connects present-day observations to the fundamental physics governing asteroid evolution over billions of years. The Chicxulub memory lingers in every asteroid orbital calculation, an invisible statistical weight that transforms abstract mathematical trajectories into reminders of the catastrophe that ended the age of dinosaurs 66 million years ago. Each newly discovered near-Earth object carries this historical burden. Its calculated impact probability and estimated damage potential measured against the benchmark of global mass extinction. The 10-kilometer impactor that created the Chicxulub crater on Mexico's Yucatan Peninsula released energy equivalent to billions of nuclear weapons, injecting enough debris into the stratosphere to block sunlight worldwide and trigger the collapse of photosynthesis-based food chains across the planet. Geological evidence from the Cretaceous-Paleogene boundary layer provides forensic details of the impact event that inform modern asteroid hazard assessments and planetary defense planning. The thin clay layer found in rock formations worldwide contains anomalous concentrations of iridium, an element rare in Earth's crust but common in asteroids and comets. This chemical signature, first identified by Nobel laureate Luis Alvarez and his team in 1980, represents the global dispersal of vaporized impactor material that settled out of the atmosphere over months or years following the collision. Impact glass spherules preserved in boundary layer sediments reveal the immediate aftermath of the Chicxulub event, when molten rock ejected from the crater solidified into tiny beads that rained down across continents and ocean basins. The size distribution and chemical composition of these spherules provide constraints on impact velocity and angle, suggesting that the asteroid struck at a near-optimal angle for maximizing global environmental disruption. A more oblique impact might have ejected less material into the stratosphere, while a head-on collision could have driven more debris completely out of Earth's gravitational influence. Shocked quartz crystals found in boundary layer rocks display microscopic deformation patterns that can only be created by the extreme pressures generated during large impact events or nuclear explosions. These mineral forensics provide independent confirmation of impact origin while constraining the pressure conditions at the moment of collision. The widespread distribution of shocked minerals demonstrates that impact pressures exceeded 1 million times atmospheric pressure across a region hundreds of kilometers from ground zero. Computer simulations of the Chicxulub impact incorporate modern understanding of hypervelocity collision physics, atmospheric dynamics, and global climate modeling to reconstruct the sequence of events that followed the initial explosion. The impactor, traveling at perhaps 20 kilometers per second, penetrated Earth's atmosphere in less than a second before striking the shallow marine environment of the Yucatan platform. The collision vaporized both the asteroid and thousands of cubic kilometers of target rock, creating a fireball that briefly outshone the sun across much of the Western Hemisphere. The immediate consequences of impact included massive tsunamis that swept across the Gulf of Mexico and Atlantic Ocean, carrying debris and marine sediments hundreds of kilometers inland. Seismic waves equivalent to magnitude 10 or 11 earthquakes propagated around the globe, triggering landslides, liquefaction, and secondary impacts that extended the zone of destruction far beyond the primary crater. Glass spherules heated by passage through the atmosphere may have ignited global wildfires that contributed additional smoke and ash to the already debris-darkened skies. Long-term environmental effects proved more devastating to global ecosystems than the immediate destruction near the impact site. Sulfur-bearing minerals in the Yucatan bedrock, when vaporized and injected into the stratosphere, formed sulfuric acid aerosols that remained suspended for years while reflecting incoming solar radiation back to space. This impact winter scenario, supported by climate modeling studies, suggests that global temperatures dropped by several degrees Celsius for extended periods, disrupting photosynthesis and collapsing food webs from marine plankton to large terrestrial vertebrates. The selectivity of Cretaceous-Paleogene extinctions provides insights into which types of organisms might survive similar future impacts, and which ecological niches prove most vulnerable to global environmental disruption. Small mammals, birds, crocodilians, and many marine invertebrates survived the extinction event, while non-avian dinosaurs, ammonites, and numerous other groups disappeared entirely from the fossil record. These survival patterns suggest that organisms with lower metabolic requirements, diverse food sources, or the ability to enter dormant states proved better adapted to the post-impact environment. Statistical analysis of crater chronology on Earth, the Moon, and other planetary bodies indicates that Chicxulub-scale impacts occur on average every 100 million to several hundred million years, making them extremely rare by human standards, yet inevitable over geological timescales. The relative youth of Earth's surface, continuously renewed by plate tectonics and erosion, means that many ancient impact craters have been destroyed or buried, making it difficult to construct complete chronologies of large impact events throughout Earth's history. Modern asteroid survey programs use Chicxulub as a calibration point for estimating the damage potential of newly discovered objects, scaling impact effects according to asteroid size, composition, and impact velocity. Objects larger than 10 kilometers in diameter remain extremely rare in near-Earth space, with perhaps fewer than a dozen such asteroids following Earth-crossing orbits. Most of these giants have been discovered and tracked, their orbital calculations indicating no significant collision probabilities for the next several centuries. The search for additional Chicxulub-scale impactors focuses primarily on long-period comets that approach from the outer solar system with minimal warning time and impact velocities potentially exceeding those of typical near-Earth asteroids. These objects, originating from the Oort cloud at distances thousands of times farther from the Sun than Earth, can appear as rapidly brightening telescopic objects that reach perihelion within months or years of discovery. Their high velocities and unpredictable arrival times pose unique challenges for planetary defense systems designed primarily to address asteroid threats. Efforts to identify and mitigate potential future Chicxulub-scale impacts must balance the extremely low probability of such events against their catastrophic consequences for human civilization and Earth's biosphere. The expected time interval between such impacts far exceeds the duration of recorded human history, yet the consequences of being unprepared for a rare but inevitable event justify continued investment in detection systems and deflection technologies. This temporal mismatch between planning horizons and threat timescales creates unique challenges for policymakers and resource allocation decisions. The Chicxulub crater itself continues to yield scientific insights about large impact processes and their effects on planetary environments. Drilling projects that penetrate the crater structure have recovered samples of impact breccia, shocked minerals, and the solidified remains of the impact melt sheet that formed when vaporized rock condensed and cooled in the aftermath of collision. These geological samples provide ground truth for computer simulations and theoretical models of hypervelocity impact physics. Recent discoveries of additional impact craters with ages similar to Chicxulub raise questions about whether the end Cretaceous extinction resulted from a single large impact or a cluster of impacts occurring within a geologically brief time interval. The Baltish crater in Ukraine and several other structures show evidence of formation within a few 100,000 years of Chicxulub, suggesting either remarkable coincidence or a common cause such as the breakup of a large asteroid or comet during its approach to the inner solar system. The Chicxulub legacy extends beyond scientific understanding to influence popular culture, policy discussions, and public awareness of cosmic hazards in ways that shape contemporary approaches to planetary defense. The dinosaur extinction scenario provides a compelling narrative that helps communicate the reality of asteroid threats to general audiences while motivating support for detection and mitigation programs. This cultural impact of paleontological research demonstrates how scientific discoveries can influence technological priorities and resource allocation decisions across multiple generations. Every asteroid that appears in telescopic surveys undergoes implicit comparison to the Chicxulub impactor, its size and orbital characteristics evaluated against the benchmark of global catastrophe that occurred at the end of the Mesozoic era. The mathematical precision of modern orbital calculations cannot eliminate the historical awareness that Earth has experienced such events before and will inevitably encounter similar threats again. The gentle irony lies in using the memory of ancient catastrophe to prevent future disasters, transforming paleontological knowledge into technological motivation for defending contemporary civilization against cosmic hazards that operate on timescales far longer than human experience. The Planetary Defense Coordination Office operates from a modest complex of buildings at NASA headquarters in Washington. Dinunko's Rikokihi Keychain, where a small team of scientists and engineers maintains humanity's official watch list of potentially hazardous asteroids with the quiet efficiency of librarians cataloging cosmic threats. Established in 2016, this unassuming bureaucratic entity serves as the United States government's focal point for coordinating asteroid detection, tracking, and potential mitigation efforts across multiple federal agencies, international partners, and civilian institutions. The office's existence represents a fundamental shift from reactive disaster response to proactive hazard management in humanity's relationship with cosmic impacts. The daily routine of planetary defense coordination involves monitoring databases that contain hundreds of thousands of asteroid observations, reviewing orbital calculations that predict future close approaches to Earth, and assessing impact probabilities that stretch decades or centuries into the future. Automated systems flag objects that warrant closer examination, while human analysts evaluate the significance of new discoveries and orbital refinements. Most days pass without significant developments, as the vast majority of asteroid observations confirm previously calculated trajectories and reinforce the low probabilities assigned to potential future impacts. Risk assessment protocols developed by the office attempt to translate the complex mathematics of orbital mechanics into actionable information for policymakers who must balance cosmic hazards against more immediate terrestrial concerns. The Torino scale provides a standardized framework for communicating asteroid threat levels, while internal technical assessments use more sophisticated analytical tools like the Palermo scale to prioritize observation campaigns and research investments. These dual communication systems acknowledge the different needs of scientific and policy communities while maintaining consistency in hazard evaluation. Congressional oversight of planetary defense activities requires regular briefings on asteroid discovery rates, orbital refinement progress, and assessments of deflection technology readiness. The office prepares annual reports that document achievements in asteroid characterization, international cooperation efforts, and technological developments relevant to potential mitigation missions. These bureaucratic requirements ensure accountability for public investments in planetary defense while maintaining political support for long-term programs that may not yield obvious benefits for decades or centuries. Interagency coordination involves multiple federal organizations with relevant expertise and resources, including the National Science Foundation's support for ground-based telescopic surveys, the Department of Defense's space surveillance capabilities, and the Department of Energy's experience with nuclear technologies that might someday be required for asteroid deflection missions. The Air Force's Space Surveillance Network contributes orbital tracking data, while NASA's Deep Space Network provides communication links for spacecraft missions to asteroid targets. International partnerships prove essential for effective planetary defense, as asteroid threats recognize no national boundaries and require global cooperation for optimal detection coverage and potential response coordination. The office maintains formal and informal relationships with space agencies, observatories, and research institutions worldwide, facilitating data sharing agreements and coordinated observation campaigns. The European Space Agency's Space Situational Awareness Program, Japan's Hayabusa asteroid missions, and numerous ground-based survey projects contribute complementary capabilities to the global planetary defense infrastructure. Technical challenges in planetary defense span multiple disciplines from astronomy and orbital mechanics to spacecraft engineering and nuclear physics. The office funds research into asteroid characterization techniques, deflection technologies, and impact consequence modeling while coordinating with university researchers and private industry partners. This broad technical portfolio reflects the interdisciplinary nature of planetary defense and the need for expertise that spans traditional academic and industrial boundaries. The office's modest budget, typically measured in tens of millions of dollars annually, must support activities ranging from telescopic surveys and data analysis to technology development and international coordination. These resource constraints require careful prioritization of activities and rely heavily on leveraging existing capabilities developed for other purposes. The efficiency of planetary defense operations demonstrates how relatively small investments in coordination and analysis can multiply the effectiveness of larger expenditures on observational facilities and technological capabilities. Communication strategies developed by the office address the challenge of maintaining public awareness and support for planetary defense without creating unnecessary alarm about low probability but high consequence events. Press releases about new asteroid discoveries emphasize the routine nature of such detections while providing context about impact probabilities and current defensive capabilities. Educational outreach programs work to improve public understanding of asteroid science and planetary defense technologies while countering misinformation propagated by sensationalist media coverage. Emergency response planning involves coordination with federal disaster management agencies to prepare for the remote possibility that an asteroid impact becomes inevitable despite detection and mitigation efforts. These contingency plans address evacuation procedures, medical response coordination, and post-impact recovery operations while acknowledging the unprecedented nature of cosmic impact disasters. The planning process draws on experience with other natural disasters while recognizing the unique characteristics of asteroid impacts that distinguish them from earthquakes, hurricanes, or volcanic eruptions. Legal and policy frameworks for planetary defense remain underdeveloped compared to other national security and disaster preparedness domains, reflecting both the low probability of asteroid impacts and the international nature of potential responses. Questions about authority for deflection missions, liability for unintended consequences of mitigation attempts, and resource allocation for global threats require careful consideration of existing treaties and domestic legislation. The Outer Space Treaty of 1967 provides some relevant provisions, but many aspects of planetary defense fall into legal gray areas that may require new international agreements. The office serves as a central repository for institutional knowledge about asteroid hazards, maintaining archives of technical reports, risk assessments, and policy analyses that preserve lessons learned and inform future decision-making processes. This documentation function proves essential for maintaining continuity across changes in political leadership and ensuring that hard-won expertise remains accessible to future planetary defense practitioners. The accumulated knowledge represents humanity's most comprehensive understanding of cosmic impact hazards and technological options for mitigation. Technology development supported by the office includes improvements to asteroid detection systems, advances in spacecraft propulsion and navigation, and research into deflection techniques ranging from kinetic impactors to gravity tractors. The DART mission to asteroid Dimorphos demonstrated the technical feasibility of kinetic deflection while providing valuable data about asteroid response to high-velocity impacts. Future technology demonstrations may explore other deflection concepts, including ion beam deflection, solar sails, or nuclear pulse propulsion. Workforce development for planetary defense involves training the next generation of scientists and engineers who will inherit responsibility for protecting Earth from cosmic hazards. The office supports university research programs, graduate student fellowships, and international exchange programs that build expertise in asteroid science, orbital mechanics, and spacecraft systems. This educational mission ensures continuity of knowledge and capabilities as current practitioners retire and new technologies emerge. The philosophical dimensions of planetary defense work extend beyond technical and policy considerations to encompass humanity's evolving relationship with cosmic hazards and technological capability. For the first time in our species' history, we possess both the knowledge to predict asteroid impacts decades in advance and the potential technological means to prevent them. This transition from passive vulnerability to active planetary protection represents a fundamental milestone in the development of technological civilization. The gentle irony of the Planetary Defense Coordination Office lies in its bureaucratic management of cosmic threats that operate on timescales far longer than typical government planning horizons. Policy documents with carefully formatted headings and bullet points address scenarios involving asteroid impacts that may not occur for centuries, while annual budget cycles fund preparations for events whose probability remains essentially zero within any individual human lifetime. Yet, this intersection of mundane administrative process with cosmic catastrophe planning reflects humanity's growing sophistication in managing low-probability, high-consequence risks through institutional mechanisms designed to maintain vigilance across multiple generations. The office continues its quiet work of monitoring, coordinating, and planning, transforming the ancient unpredictability of cosmic hazards into manageable technological and policy challenges through the patient application of scientific knowledge and bureaucratic organization. Each day's routine activities contribute incrementally to humanity's expanding capability for planetary protection, building the institutional foundations that may someday prevent a cosmic catastrophe through the accumulated efforts of thousands of dedicated individuals working within the measured pace of democratic institutions and international cooperation. Close approaches unfold across the cosmic distance scale with mathematical precision, their proximity measured in multiples of the Moon's orbital radius as asteroids sweep past Earth along trajectories calculated years in advance. The lunar distance, approximately 384,400 kilometers or 238,855 miles, serves as the fundamental unit for describing these celestial near misses, providing an intuitive reference point that places asteroid encounters in context with humanity's most familiar cosmic neighbor. Objects that pass within 10 lunar distances and classification as close approaches worthy of special observation, while those venturing within 5 lunar distances trigger intensive monitoring campaigns by telescopes worldwide. The geometry of close approaches depends on the three-dimensional intersection of orbital planes as Earth and Asteroid follow their respective elliptical paths around the Sun. Most near-Earth asteroids travel in orbits tilted at various angles relative to Earth's orbital plane, creating approach geometries where the objects may pass above, below, or alongside our planet's trajectory through space. The closest approach distance represents the minimum separation achieved as the two bodies sweep past each other, a value that remains fixed by orbital mechanics regardless of when the encounter occurs within human observation timelines. Observational opportunities during close approaches provide astronomers with enhanced capabilities for detailed asteroid characterization, as proximity dramatically improves the apparent brightness and angular resolution achievable by Earth-based telescopes. An asteroid that normally appears as a point source, indistinguishable from background stars, may reveal surface features, rotation characteristics, and spectroscopic details when observed during its closest approach to Earth. These enhanced observation windows often represent the best opportunities for decades to study specific objects in detail. Radar astronomy reaches peak effectiveness during the closest asteroid approaches, when round-trip signal travel times drop to manageable durations and reflected signal strength increases according to inverse square law physics. The Goldstone planetary radar system can detect objects out to several million kilometers, but detailed imaging capabilities remain limited to asteroids passing within a few 100,000 kilometers of Earth. During exceptionally close approaches, radar observations can resolve surface features smaller than 10 meters across, revealing geological details invisible to optical telescopes. The statistical frequency of close approaches follows predictable patterns based on the orbital characteristics and population estimates of near-Earth asteroids. Objects larger than 1 kilometer approach within 10 lunar distances approximately once every few years, while smaller asteroids in the 50-meter size range may pass this close several times annually. The steady cadence of close approaches provides regular opportunities for improving asteroid observations while demonstrating the active nature of Earth's cosmic neighborhood. Media attention focused on close approaches often creates public concern disproportionate to actual impact risks, as news reports emphasize the dramatic aspects of cosmic near misses without adequate context about the vast distances involved. An asteroid passing at twice the lunar distance remains more than twice as far from Earth as any human has ever traveled. Yet headlines describing close shaves or near misses can create impressions of immediate danger where none exists. Educational efforts by planetary defense organizations attempt to provide proper perspective on close approach distances and their relationship to genuine impact threats. Gravitational perturbations during close approaches modify asteroid orbits in subtle but measurable ways, creating opportunities to study how planetary encounters influence long-term orbital evolution. Earth's gravitational field deflects passing asteroids onto new trajectories that may increase or decrease future collision probabilities depending on the specific geometry of each encounter. These natural deflection experiments provide valuable data for validating theoretical models of gravitational scattering and assessing the effectiveness of proposed deflection technologies. The Öpik-Arnold theory describes the mathematical framework for calculating how close planetary encounters scatter asteroid orbits into new configurations, providing statistical predictions about post-encounter trajectories and collision probabilities. Named after Estonian astronomer Ernst Öpik and American mathematician James Arnold. This theoretical approach treats each close approach as a random scattering event that distributes asteroids across a range of possible future orbits. The theory helps explain both the observed orbital distribution of near-Earth asteroids and the chaotic evolution of individual object trajectories over long time scales. Binary asteroid systems often undergo dramatic changes during close planetary encounters, as tidal forces from Earth's gravity can disrupt the weak gravitational bonds holding these systems together. The critical distance for tidal disruption depends on the size ratio and separation of the binary components, with some loosely bound systems breaking apart when they pass within several Earth radii of our planet's center. These tidal disruption events create new single asteroids with orbital characteristics that may differ significantly from the original binary system. Photometric observations during close approaches can detect subtle brightness variations caused by the changing viewing geometry as Earth's position relative to the asteroid shifts throughout the encounter. Phase angle effects. Similar to the Moon's phases but occurring over much shorter timescales, create systematic brightness changes that reveal information about asteroid surface properties and scattering characteristics. These geometric effects must be carefully accounted for when interpreting photometric data collected during close-approach observation campaigns. Spectroscopic studies benefit enormously from the enhanced signal-to-noise ratios achievable during close approaches, allowing detailed analysis of asteroid surface composition and mineralogy that would be impossible at greater distances. Near-infrared spectroscopy can detect absorption features corresponding to specific mineral phases, while visible wavelength observations reveal subtle color variations that indicate space weathering processes or compositional heterogeneity. These detailed compositional studies contribute to understanding of asteroid formation conditions and evolutionary processes. Amateur astronomers worldwide contribute valuable observations during asteroid close approaches, using modest telescopes and CCD cameras to track object positions and measure brightness variations. These citizen science contributions complement professional observations while providing geographic distribution of observation sites that improve orbital determinations. The involvement of amateur observers demonstrates how close approaches create opportunities for broad participation in asteroid research and planetary defense activities. Astrometric measurements during close approaches provide the most precise positional data available for refining asteroid orbital calculations, as the enhanced apparent motion against background stars allows more accurate determination of trajectory parameters. Small improvements in orbital precision achieved during close approaches can significantly reduce uncertainty in long-term predictions, sometimes ruling out previously calculated impact possibilities or identifying new potential collision scenarios. These orbital refinements represent one of the most valuable scientific outcomes of close approach observations. Space missions to asteroids often target objects during or shortly before close approaches, taking advantage of reduced travel times and enhanced communication capabilities when spacecraft operate relatively close to Earth. The near-Shoemaker mission to asteroid Eros and the recent DART mission to Dimorphos both involved operations during periods when their target asteroids passed within the inner solar system. Future deflection missions will likely require similar timing to maximize spacecraft capability while minimizing mission duration and complexity. The psychological impact of widely publicized close approaches extends beyond immediate public concern to influence long-term attitudes toward asteroid threats and planetary defense priorities. Dramatic close approaches that receive extensive media coverage often generate increased public interest in asteroid research and support for detection programs, creating political momentum for expanded funding and international cooperation. These events serve as natural experiments in risk communication and public engagement with low probability, high consequence hazards. Orbital resonances can create periodic close approaches where the same asteroid repeatedly returns to Earth's vicinity at regular intervals determined by the mathematical relationship between orbital periods. The asteroid 99942, Apophis, follows an orbit that produces close approaches approximately every 7 years, with the 2029 encounter predicted to carry it within 31,000 kilometers of Earth's surface, closer than many artificial satellites. Such predictable encounter series provide multiple opportunities for detailed study while testing theoretical models of orbital evolution and tidal effects. The gentle irony of asteroid close approaches lies in their simultaneous intimacy and remoteness, bringing ancient wanderers of the cosmos closer to Earth than they have been for millions of years, while still maintaining distances that exceed the reach of human space travel by enormous factors. These cosmic visitors sweep past our planet following laws of physics that operate with clockwork precision across the vast scales of space and time. Their brief proximity offering fleeting opportunities to study remnants of the early solar system before they continue their patient journeys through the darkness of interplanetary space. The DART mission arrives at its target with the velocity of a bullet, traveling at 14 kilometers per second when it strikes the surface of Dimorphos, a small asteroid moon orbiting its larger companion, Didymos, in the gentle gravitational dance of a binary system. The collision occurs on September 26, 2022, after a journey of nearly 10 months through interplanetary space, culminating in humanity's first deliberate attempt to alter the trajectory of a celestial body through kinetic impact. The spacecraft, no larger than a small automobile and weighing just 610 kilograms, carries the accumulated hopes of planetary defense planners worldwide as it approaches its rendezvous with ancient cosmic debris. The impact crater created by DART's collision reveals itself through ground-based telescopic observations that detect subtle changes in the binary system's orbital characteristics. Dimorphos, originally completing one orbit around Didymos every 11 hours and 55 minutes, begins moving in a slightly tighter orbit with a period shortened by approximately 32 minutes. This seemingly modest change represents a dramatic success for kinetic deflection theory, demonstrating that small spacecraft can indeed impart measurable momentum changes to much larger asteroids through carefully planned high-velocity impacts. The physics of hypervelocity impact involves complex interactions between spacecraft materials and asteroid surface composition that challenge theoretical predictions about momentum transfer efficiency. When DART strikes Dimorphos at more than 6 kilometers per second, the collision generates pressures and temperatures that vaporize both the spacecraft and substantial amounts of target material, creating an expanding cloud of hot gases and debris that continues to exert force on the asteroid long after the initial impact. This enhanced momentum transfer, caused by the rocket-like effect of escaping impact ejecta, proves more efficient than simple conservation of momentum calculations would predict. Observations from ground-based telescopes reveal a dramatic brightening of the Didymos system following impact, as sunlight reflects off the expanding debris cloud ejected from Dimorphos during the collision. The ejecta plume remains visible for weeks, gradually dispersing into space while providing astronomers with unprecedented data about asteroid internal structure and composition. Spectroscopic analysis of the debris reveals mineralogical information about Dimorphos that would be impossible to obtain through remote observations of the intact surface. The European Space Agency's Hera mission, scheduled to arrive at the Didymos system in 2026, will provide detailed post-impact reconnaissance of the DART crater and surrounding terrain. This follow-up investigation will measure the precise dimensions of the impact feature, analyze the distribution of ejected material, and assess any structural changes to Dimorphos caused by the collision. The comprehensive post-impact survey will validate theoretical models of kinetic deflection while providing essential data for planning future asteroid deflection missions. Binary asteroid systems like Didymos Dimorphos present unique opportunities for kinetic deflection experiments. As changes in orbital motion become apparent through variations in mutual eclipse timing that can be measured from Earth using modest telescopes, the binary configuration transforms subtle momentum changes into observable orbital modifications, providing a natural amplification system that makes DART's effects detectable across millions of miles of interplanetary space. Single asteroids would require much more sensitive measurements to detect comparable deflection results. The selection of Dimorphos as DART's target reflects careful consideration of both scientific objectives and planetary protection requirements. The asteroid's orbit around Didymos ensures that any changes induced by the impact cannot alter the system's trajectory relative to Earth, eliminating concerns that the deflection experiment might inadvertently create a new impact hazard. This containment within the binary system allows researchers to study kinetic deflection effects without introducing new risks to Earth's environment. Momentum enhancement factors measured during the DART impact exceed theoretical predictions by significant margins, suggesting that kinetic deflection may prove more efficient than conservative estimates indicated. The beta factor, which quantifies the ratio between actual momentum change and the momentum of the impacting spacecraft, reaches values of approximately 3.6 for the DART collision. This enhanced efficiency results from the contribution of high-velocity ejecta that amplifies the momentum transfer beyond simple billiard ball collision physics. The rubble pile structure of many asteroids, including Dimorphos, creates complex internal responses to kinetic impacts that may enhance or reduce deflection efficiency depending on target properties and impact conditions. Loosely consolidated debris held together primarily by weak gravitational attraction responds differently to high-velocity collisions than solid, monolithic rocky bodies. The DART results provide the first empirical data about how realistic asteroid targets behave under kinetic deflection conditions. Scaling laws derived from DART mission results enable predictions about deflection efficiency for impacts involving different asteroid sizes, impact velocities, and spacecraft masses. These mathematical relationships allow mission planners to design future deflection systems optimized for specific asteroid characteristics and deflection requirements. The empirical validation of kinetic deflection theory transforms speculative planetary defense concepts into engineering problems with quantifiable solutions and predictable outcomes. International collaboration in planetary defense receives dramatic demonstration through the DART mission's success, as observatories around the globe contribute complementary observations that collectively determine the mission's effectiveness. Ground-based telescopes in multiple countries track orbital changes, while space-based assets provide additional confirmation of impact results. This coordinated observation campaign demonstrates the global nature of planetary defense and the benefits of international cooperation in addressing cosmic threats. The technological heritage of DART draws from decades of spacecraft development for other mission objectives, adapting existing propulsion, navigation, and communication systems for the specialized requirements of asteroid intercept and impact. The autonomous navigation system that guides DART to its target during the final approach phase builds on technologies developed for landing spacecraft on Mars and other planetary bodies. This technological cross-fertilization demonstrates how investments in space exploration capabilities support multiple mission objectives, including planetary defense. Impact timing calculations for DART require extraordinary precision in trajectory prediction and navigation, as the spacecraft must arrive at a specific point in space at the exact moment when Dimorphos occupies that same location. The mission's success validates advanced orbital mechanics calculations and autonomous navigation capabilities that will prove essential for future deflection missions. Any significant errors in timing or targeting would have resulted in a complete mission failure with no opportunity for correction. The cost-effectiveness of kinetic deflection, demonstrated by DART's relatively modest budget compared to the scale of its achievement, suggests that planetary defense capabilities may be more affordable than previously estimated. The mission's success with a single spacecraft costing less than $330 million demonstrates that effective asteroid deflection does not necessarily require massive technological investments or international megaprojects. This economic feasibility enhances the political viability of developing operational planetary defense systems. Future kinetic deflection missions may employ multiple spacecraft to achieve larger momentum changes or to provide redundancy against individual mission failures. Swarm concepts involving dozens of small impactors could distribute deflection effects across asteroid surfaces while providing statistical confidence in overall mission success. Alternative approaches might use larger spacecraft or higher impact velocities to maximize momentum transfer efficiency for particularly challenging deflection scenarios. The DART mission transforms planetary defense from theoretical speculation into demonstrated technological capability, providing empirical proof that human civilization possesses the tools necessary to protect Earth from at least certain categories of asteroid threats. This technological milestone represents a fundamental transition in humanity's relationship with cosmic hazards, from passive vulnerability to active planetary protection through the application of advanced spacecraft systems and precise orbital mechanics calculations. The gentle irony of humanity's first asteroid deflection lies in its use of controlled destruction to achieve protection, deliberately destroying a sophisticated spacecraft in a violent collision to demonstrate our species' growing capability for cosmic construction through apparent cosmic vandalism. The DART mission's success validates theoretical models while opening new chapters in both asteroid science and planetary defense, transforming ancient wanderers of the cosmos into subjects for human technological manipulation across the vast scales of interplanetary space. The momentum transfer continues to propagate through Dimorphos as gravitational forces gradually redistribute the impact's effects throughout the asteroid's rubble pile structure, while the modified orbital mechanics carry the binary system along its new trajectory around the Sun. The consequences of that brief moment of contact between human technology and primordial asteroid material will persist for millions of years, a permanent alteration in the cosmic dance that began when the solar system first formed from the collapse of an ancient stellar nursery. International networks span the globe like an invisible web of cooperation, their telescopes and tracking stations coordinating observations across time zones and hemispheres to ensure that no patch of darkness remains unwatched for extended periods. The Minor Planet Center in Cambridge, Massachusetts, serves as the central nervous system for this distributed detection network, receiving and processing more than 1 million asteroid observations each year from professional observatories, government facilities, and amateur astronomers scattered across 6 continents. This remarkable coordination transforms individual telescope observations into a comprehensive global monitoring system that operates with the efficiency of a single, planet-spanning instrument. The Earth's rotation creates natural complementarity between observing sites separated by longitude. As the approach of dawn at one facility coincides with the onset of darkness at locations roughly 12 hours to the west, this geometric relationship allows continuous monitoring of critical asteroid targets as they move across the sky, with observations passing seamlessly from Asian observatories to European facilities to American installations throughout each 24-hour period. The global network effectively extends observing time beyond the limitations imposed by local weather and daylight cycles. Data sharing protocols developed by the International Astronomical Union ensure standardized formatting and rapid dissemination of asteroid observations across institutional and national boundaries. Electronic communication systems transmit positional measurements, photometric data, and preliminary orbit calculations within minutes of observation, allowing near real-time coordination of follow-up observations and target prioritization. These technical standards, refined through decades of international collaboration, enable seamless integration of observations from telescopes with different designs, calibrations, and measurement capabilities. The European Space Agency's Space Situational Awareness Program contributes specialized capabilities for tracking objects in near-Earth space, complementing traditional astronomical surveys with technologies adapted from military space surveillance systems. Radar installations and optical telescopes designed for satellite monitoring can detect and track asteroids during their closest approaches to Earth, providing precise astrometric measurements that improve orbital calculations. This dual-use approach leverages existing infrastructure investments while contributing to global planetary defense capabilities. Amateur astronomers worldwide provide essential contributions to international asteroid monitoring through coordinated observation campaigns that utilize relatively modest equipment to achieve scientifically valuable results. The SpaceGuard Australia Network, European amateur asteroid observers, and similar groups in Asia and the Americas demonstrate how distributed citizen science can supplement professional survey programs. These volunteers often provide crucial follow-up observations that confirm new discoveries and refine orbital calculations for objects discovered by automated survey systems. Seasonal variations in asteroid visibility create coordination challenges that require careful planning to maintain comprehensive sky coverage throughout Earth's orbital cycle. Objects with orbits similar to Earth's may remain visible primarily during certain times of year, creating observation windows that must be shared efficiently among available telescopes. International cooperation proves essential for maximizing these limited opportunities, with observatories scheduling complementary observation programs that ensure adequate temporal coverage of high-priority targets. Language barriers and cultural differences present ongoing challenges for international asteroid monitoring coordination. Despite the universal language of mathematical orbital elements and standardized observation formats, scientific collaboration requires clear communication about observation priorities, data quality standards, and resource allocation decisions that affect multiple institutions and national programs. Regular international workshops and electronic communication forums help maintain the personal relationships that facilitate effective technical cooperation. The Global Challenges Foundation and similar organizations have identified asteroid impacts among the existential risks that require coordinated international responses, transcending traditional national security frameworks. These policy analyses emphasize that asteroid threats affect all nations equally regardless of geographic location, economic development, or political systems. The global nature of potential impact consequences necessitates cooperation mechanisms that can function effectively even during periods of international tension or conflict. Funding disparities between developed and developing nations create imbalances in global asteroid monitoring capabilities, with most major survey programs concentrated in wealthy countries with established space science infrastructure. International development assistance and technology transfer programs attempt to address these disparities by supporting observatory construction and training programs in regions currently underrepresented in global monitoring networks. The expansion of geographic coverage improves asteroid detection capabilities while building scientific capacity in emerging spacefaring nations. The United Nations Office for Outer Space Affairs coordinates international discussions about planetary defense policies and procedures, providing a diplomatic forum for addressing the legal and political dimensions of asteroid threat mitigation. These multilateral dialogues address questions about authority for deflection missions, liability for unintended consequences, and resource-sharing arrangements for global monitoring programs. The development of international frameworks for planetary defense represents a unique challenge in global governance, requiring unprecedented cooperation on low probability but high consequence risks. Technological standardization efforts aim to improve interoperability between different national and institutional monitoring systems while preserving the benefits of technical diversity that emerges from independent development programs. Common communication protocols, calibration standards, and data formats enable more efficient coordination while allowing individual facilities to pursue innovative approaches to asteroid detection and characterization. This balance between standardization and innovation reflects the complex dynamics of international scientific collaboration. Time zone coordination proves surprisingly complex for global asteroid monitoring networks, as optimal observation scheduling must account not only for target visibility, but also for personnel availability, equipment maintenance schedules, and competing observational priorities. Automated systems reduce the burden of round-the-clock coordination, but human oversight remains essential for making rapid decisions about target prioritization and observation strategy adjustments. The development of efficient coordination protocols represents an ongoing challenge for international collaboration. Emergency communication procedures ensure rapid dissemination of information about newly discovered potentially hazardous asteroids to relevant national authorities and international organizations. These alert systems must balance the need for timely notification against the importance of verification and quality control to avoid false alarms that could trigger inappropriate responses. The protocols recognize that asteroid impact warnings may require coordination with emergency management agencies, military organizations, and civil defense authorities beyond the traditional astronomical community. Regional observatory networks in Europe, Asia, and the Americas provide intermediate levels of coordination between individual facilities and global monitoring systems, allowing more efficient resource sharing and observation planning within geographic regions. These regional partnerships often share common languages, time zones, and institutional cultures that facilitate closer cooperation while contributing to broader international coordination efforts. The nested structure of local, regional, and global coordination reflects the complex organizational requirements of truly international scientific collaboration. Quality control mechanisms ensure that observations contributed by international partners meet scientific standards necessary for reliable orbital calculations and hazard assessments. Automated data validation systems check for internal consistency, comparison with theoretical predictions, and compatibility with observations from other facilities. These technical safeguards protect the integrity of global asteroid databases while accommodating the diverse capabilities and calibration standards of contributing observatories worldwide. The success of international asteroid monitoring demonstrates the feasibility of global cooperation on scientific challenges that transcend national boundaries and require sustained collaboration over decades or centuries. The patient work of data sharing, observation coordination, and technical standardization provides a model for addressing other global challenges that require similar long-term international cooperation. The Asteroid Monitoring Network represents one of humanity's most successful examples of peaceful international collaboration in space-related activities. Cultural exchange programs and scientific visitor arrangements strengthen the personal relationships that underpin effective international coordination in asteroid monitoring. Young researchers who train at foreign observatories and participate in international workshops often become key figures in maintaining cooperative relationships throughout their careers. These human connections prove essential for resolving technical disputes, coordinating emergency responses, and maintaining collaboration during periods of political tension between nations. The gentle irony of international asteroid monitoring lies in its transformation of ancient cosmic wanderers into subjects for modern diplomatic cooperation, requiring nations to coordinate their responses to threats that recognize no political boundaries or territorial claims. The same objects that have drifted through space for billions of years without regard for human civilization now serve as focal points for international collaboration that may prove essential for humanity's long-term survival in a cosmos filled with both wonders and hazards that operate according to the impartial laws of celestial mechanics. Cosmic archaeology unfolds in real time as each newly discovered asteroid receives its permanent numerical designation, transforming ancient fragments of planetary formation into catalogued entries in humanity's expanding database of solar system debris. The process begins with preliminary designations assigned immediately upon discovery alphanumeric codes that indicate the year and half-month of first observation, along with sequential letters marking the order of detection within each time period. These temporary labels, resembling cryptic astronomical license plates, eventually give way to permanent numbers awarded only after orbital calculations achieve sufficient precision to guarantee reliable future recovery of each object. The Minor Planet Center maintains this cosmic census with the methodical precision of a vast bureaucratic enterprise, processing hundreds of new discoveries each month while refining the orbits of hundreds of thousands of previously catalogued objects. Each asteroid begins its journey through the designation system as nothing more than a series of coordinate measurements, right ascension, declination, and apparent magnitude recorded at specific times by telescopic observers around the globe. These numerical breadcrumbs, when accumulated over weeks or months of observation, reveal the invisible elliptical paths that carry each object through its eternal dance around the Sun. Orbital determination transforms scattered observational data points into comprehensive mathematical descriptions of asteroid trajectories, calculating the 6 orbital elements that completely specify each object's motion through 3-dimensional space. The semi-major axis describes the size of the elliptical orbit, while eccentricity quantifies how elongated or circular that ellipse appears. Inclination measures the tilt of the orbital plane relative to Earth's path around the Sun, and the longitude of ascending node indicates where the asteroid's orbit crosses the ecliptic plane. These geometric parameters, determined to many decimal places, contain enough information to predict an asteroid's position at any moment throughout its orbital period. The permanent numbering system reflects humanity's gradual accumulation of knowledge about the solar system's small body population, with sequential integers assigned in rough chronological order of orbital conformation. Asteroid number 1, Ceres, received its designation in 1801 when Giuseppe Piazzi first spotted this largest member of the main asteroid belt from his observatory in Palermo, Sicily. The sequence has continued uninterrupted for more than 2 centuries, reaching beyond 500,000 confirmed objects as modern survey programs discover thousands of new asteroids annually. Named asteroids represent a small fraction of the total catalog population, as the privilege of assigning proper names remains reserved for objects whose orbits have been determined with exceptional precision over extended observation periods. The naming process follows strict guidelines established by the International Astronomical Union, prohibiting names of military leaders, commercial products, or purely commercial enterprises, while encouraging designations that honor scientists, cultural figures, or geographic locations. Most asteroids remain known only by their numerical designations, anonymous wanderers identified solely by their position in humanity's cosmic catalog. Physical characterization extends beyond simple orbital mechanics to include detailed studies of asteroid composition, structure, and rotation characteristics derived from photometric, spectroscopic, and radar observations. Taxonomic classification systems group asteroids into families based on spectral similarities that reflect common compositional characteristics, with S-type objects dominated by silicate minerals and C-type asteroids containing higher concentrations of carbon-bearing compounds. These classification schemes provide insights into formation conditions throughout the early solar system, while identifying potentially valuable targets for future resource exploitation missions. The temporal dimension of asteroid cataloging reveals humanity's accelerating capability for cosmic census-taking, with discovery rates increasing exponentially as digital imaging technology and automated detection algorithms revolutionize survey efficiency. The first century of asteroid astronomy, from 1801 to 1900, produced fewer than 500 confirmed discoveries, while modern survey programs now catalog similar numbers of new objects every few days. This acceleration reflects not only technological advancement, but also growing awareness of the importance of comprehensive situational awareness regarding near-Earth space. Database management for hundreds of thousands of asteroid observations requires sophisticated computational infrastructure capable of storing, processing, and disseminating enormous volumes of astrometric data. The Minor Planet Center's electronic databases contain millions of individual position measurements accumulated over decades of international observational campaigns, each data point contributing to the slowly improving precision of orbital calculations for catalogued objects. Modern database systems enable rapid queries and statistical analyses that would have been impossible during the era of printed catalogs and manual calculations. Quality control procedures ensure the reliability of asteroid catalogs by detecting and correcting observational errors, instrumental artifacts, and computational mistakes that inevitably accumulate during large-scale data processing operations. Automated algorithms flag measurements that deviate significantly from predicted positions, while human reviewers examine potentially problematic observations and coordinate follow-up observations when necessary. These verification processes maintain the scientific integrity of astronomical databases while accommodating the diverse capabilities and calibration standards of contributing observatories worldwide. Statistical analysis of the completed portions of asteroid catalogs provides insights into the size distribution, orbital characteristics, and compositional diversity of small bodies throughout the inner solar system. Power law relationships describe how asteroid abundance varies with size, revealing the fingerprints of collisional evolution processes that have shaped the small body population over billions of years. These statistical patterns inform theoretical models of planetary formation while providing baseline expectations for future discoveries, as survey programs extend their reach to smaller and more distant objects. The asteroid catalog serves multiple communities with different requirements and interests, from professional astronomers studying solar system evolution to planetary defense specialists assessing impact hazards to commercial organizations evaluating potential asteroid mining targets. Each user community requires different types of information and different levels of precision, creating ongoing challenges for database designers who must balance comprehensive data preservation with efficient access and user-friendly interfaces. The democratization of asteroid data through online databases has transformed what was once specialized knowledge accessible only to professional astronomers into publicly available information that supports education, research, and commercial development. Archival preservation ensures that decades of accumulated asteroid observations remain accessible to future researchers, even as technological systems evolve and institutional responsibilities change. Digital preservation strategies address the challenges of format obsolescence, hardware failure, and institutional continuity that threaten long-term data accessibility. The asteroid database represents one of astronomy's most valuable long-term datasets, containing observational records that span more than 2 centuries of systematic sky surveys. International coordination of catalog maintenance involves complex agreements about data sharing, quality standards, and designation authority that reflect both scientific requirements and diplomatic considerations. The Minor Planet Center's role as the internationally recognized authority for asteroid designations represents a remarkable example of successful global governance in scientific matters, maintaining consistent standards and procedures despite the involvement of dozens of countries and hundreds of institutions. This coordination system has proven remarkably stable and effective over multiple decades of operation. The future expansion of asteroid catalogs will be driven by next-generation survey systems capable of detecting much smaller and more distant objects than current facilities can reliably observe. The Vera Rubin Observatory, scheduled to begin operations in the mid-2020s, may discover more asteroids during its first year of operation than humanity has catalogued throughout all previous history. These expanded catalogs will provide unprecedented statistical samples for studying solar system formation while identifying potential targets for scientific missions and commercial exploitation. Each newly catalogued asteroid carries within its orbital elements and physical characteristics a unique story spanning billions of years of solar system evolution. From its formation in the primordial solar nebula, through countless gravitational encounters and collisional interactions that have shaped its current trajectory through space. The catalog transforms these individual stories into collective knowledge about planetary formation processes, asteroid belt evolution, and the ongoing dynamics that continue to transport ancient debris into Earth's cosmic neighborhood. The gentle irony of cosmic archaeology lies in its preservation of ephemeral human observations to study objects that have existed since the dawn of the solar system. Creating permanent digital records of temporary gravitational relationships that describe ancient wanderers whose stories began billions of years before human consciousness evolved to catalog their existence. Each database entry represents a moment of intersection between human curiosity and cosmic wandering, preserving numerical descriptions of celestial mechanics that will outlast the individual astronomers who contributed to their discovery and characterization. The catalog continues to grow each night as automated survey systems process the previous evening's observations, adding new entries to humanity's expanding awareness of its cosmic neighborhood while refining the orbital knowledge of previously discovered objects through additional position measurements that improve long-term predictive accuracy. The endless quiet of systematic observation settles over mountain peaks and desert valleys where telescopes maintain their patient vigil, their mechanical precision unaffected by the passage of seasons or the turning of years. In the deepest hours before dawn, when the last observations of each night approach completion and the eastern sky begins its imperceptible brightening, the accumulated data flows silently through fiber optic cables toward processing centers where algorithms will spend the coming day searching for signs of cosmic motion against the apparently fixed backdrop of distant stars. The rhythm of discovery follows cycles older than human civilization, governed by Earth's rotation and orbital motion around the Sun, yet measured now in gigabytes of digital imagery and millions of mathematical calculations performed with electronic precision. Each night's work adds incremental contributions to humanity's growing catalog of near-Earth objects, expanding the boundaries of knowledge through observations so routine they have become almost mundane, yet collectively representing one of our species' most comprehensive surveys of any natural phenomenon. Ancient starlight mingles with the thermal glow of asteroids formed billions of years ago in the cosmic darkness. Their faint electromagnetic signatures, captured by sensors, cooled to near absolute zero and processed by computers that can detect motion invisible to human perception. The photons that trigger these electronic cascades have traveled across millions of miles of empty space, carrying encoded information about surface temperatures, mineral compositions, and rotational dynamics that reveal the hidden stories of objects too small and distant for direct examination. Statistical certainty emerges gradually from the accumulation of individual observations, each measurement contributing small improvements to orbital calculations that slowly converge toward mathematical precision, limited only by the fundamental uncertainties imposed by chaos theory and the complex gravitational environment of the inner solar system. The process requires patience measured in months or years. As preliminary orbital solutions refined through hundreds of additional position measurements transform tentative discoveries into permanent catalog entries with precisely determined trajectories. Professional astronomers and citizen scientists continue their coordinated observations from locations scattered across the globe, their diverse telescopes and detection systems contributing to a monitoring network that operates with the distributed efficiency of a biological nervous system. The democratization of astronomical instrumentation has enabled contributions from observers using equipment that would have seemed impossibly sophisticated just decades ago, yet now represents technology accessible to dedicated amateurs willing to invest time and modest resources in planetary defense activities. The bureaucratic machinery of international coordination processes this constant stream of observational data through standardized protocols that transform individual telescope measurements into collective knowledge accessible to researchers worldwide. Electronic communication systems designed for near-instantaneous global data sharing ensure that important discoveries receive rapid confirmation and follow-up observation, while automated quality control algorithms filter out instrumental artifacts and observational errors that would otherwise contaminate the accumulated databases. Technological evolution continues to accelerate the pace of discovery as next-generation survey systems prepare to begin operations with sensitivity and sky coverage capabilities that will dwarf current facilities. The transition from photographic plates to digital detectors revolutionized asteroid astronomy during the final decades of the 20th century, and similar transformations await as artificial intelligence algorithms and space-based survey missions extend human perception deeper into the cosmic darkness surrounding Earth's orbital neighborhood. The mathematical precision of celestial mechanics provides reassurance that asteroid trajectories can be calculated with remarkable accuracy across spans of decades or centuries. Yet the fundamental limitations imposed by chaotic dynamics ensure that perfect long-term prediction will always remain beyond reach. This balance between knowledge and uncertainty reflects the broader human condition of scientific understanding, where precise measurements and theoretical sophistication coexist with irreducible mysteries about the ultimate fate of individual objects over astronomical timescales. Gravitational perturbations and thermal forces continue their patient work of orbital modification, operating according to physical laws that remain unchanged since the formation of the solar system billions of years ago. Each asteroid follows its predetermined path through space while simultaneously participating in the gradual evolution of orbital characteristics that will eventually transport some objects to dangerous Earth-crossing trajectories and others to safe ejection from the inner solar system entirely. The cosmic perspective reveals humanity's growing technological capability for planetary protection within the vast context of astronomical time and space, where our most sophisticated achievements remain dwarfed by the scales on which natural processes operate. Yet, within these cosmic proportions, the patient accumulation of knowledge and the development of deflection technologies represent genuine milestones in the evolution of technological civilization's relationship with its cosmic environment. International cooperation in asteroid monitoring demonstrates humanity's capacity for sustained collaboration on challenges that transcend national boundaries and require planning horizons that extend far beyond typical political cycles. The success of this global coordination provides hope that similar cooperative mechanisms might address other planetary-scale challenges requiring long-term commitment and shared resources from the international community. The asteroid catalog continues its steady growth as each clear night adds new discoveries and refined orbital calculations to the accumulated knowledge base that represents humanity's most complete census of any category of natural hazard. This systematic approach to cosmic threat assessment transforms unpredictable celestial catastrophes into manageable risks subject to quantitative analysis, early warning systems, and potential technological mitigation through carefully planned spacecraft missions. The gentle persistence of automated survey systems embodies humanity's commitment to maintaining vigilant awareness of cosmic hazards across timescales that exceed individual lifetimes, creating institutional knowledge and technological capabilities that will serve future generations regardless of changes in political leadership or economic priorities. The telescopes continue their scanning motions with mechanical reliability, their electronic sensors recording the faint light that carries information across the vast emptiness of interplanetary space. In the moments before sunrise forces the closure of protective telescope covers. The last observations of each night join millions of previous measurements in databases that preserve humanity's expanding awareness of its cosmic neighborhood. The work continues without fanfare or dramatic conclusion, driven by the quiet recognition that comprehensive situational awareness requires sustained commitment to systematic observation and international cooperation across decades of patient effort. The darkness gradually yields to approaching dawn as Earth's rotation carries observation sites into daylight, ending another night's contribution to humanity's ongoing census of near-Earth objects. Processing systems begin their daily analysis of accumulated data, while telescopes on the planet's night side continue the work, maintaining the global coverage that ensures no potentially hazardous asteroid approaches Earth without detection and careful tracking by the international community of observers dedicated to planetary defense. The ancient wanderers continue their journeys through the cosmic darkness, their paths governed by gravitational forces and orbital mechanics that operate with mathematical precision across the vast scales of space and time, while human technology gradually expands its capability for detection, characterization, and potential deflection of objects that might someday threaten the continued evolution of life on Earth.